So welcome students to the topic of polynomial equations. Polynomials are a very important types of expressions that we encounter in our mathematical problems. So let us see what a polynomial is. So a polynomial is an expression of the form an x power n plus an minus 1 x to the power n minus 1 plus an minus 2 x to the power n minus 2 plus so on plus a1x plus a0. So an expression of this form where n belongs to whole numbers and the coefficients a0, a1, a2, so on up to an belong to some number system f is called a polynomial in the variable x over the number system f. So an expression of this form where this n belongs to whole numbers and a0, a1, a2 up to an, the coefficients of different powers of x belongs to some number system is called a polynomial in the variable x over the number system f. So polynomials are usually denoted by f of x or g of x, so on, where f is the name of the polynomial and the variable inside the bracket is the variable over which the polynomial is defined. If the polynomial is defined in the variable y, we write it as f of y or g of y or a of y, whatever you want to write. So this is the definition of a polynomial. The important thing that you need to observe is that the powers of x that are there in polynomial, the powers of x that are there in polynomial are always whole numbers. You cannot have fractional powers of x. Next, if the numbers a0, a1, a2, so on up to an belongs to the set of real numbers, so they can belong to any set f, any number set f, and the polynomial is defined on that set f. So if these coefficients belong to real numbers, then the polynomial which we have is called a real polynomial. If all the numbers of all the coefficients of different powers of x are all real, then the polynomial is called a real polynomial. If all of them are, if all the coefficients belong to a set of complex numbers, then it is called a complex polynomial. So if a0, a1, a2, so on up to an belong to the set of complex numbers, then the polynomial is called a complex polynomial. So you can have these coefficients in any set. So whatever this set to which these coefficients belong, we say that this is a polynomial over that set. And the highest power of x present in the polynomial is called the degree of the polynomial. Degree of the polynomial is the highest power of x. Highest power of x with a non-zero coefficient, present in the polynomial. So that is called the degree of the polynomial. So let us take some examples. So if you take an example, 2x square plus 3x minus 5 is a polynomial in the variable x and the degree of this polynomial is 2. because x power 2 is the highest power of x present in this expression. So this is a polynomial in the variable x. So if you have 3y cube plus 2y plus 6, this is a polynomial of degree 3, and this is a polynomial defined in the variable y. So if you have an expression x plus 1 by x, this is not a polynomial because x power 1 is okay, but 1 by x is x power minus 1. The powers of x are not all whole numbers. Hence, this is not a polynomial. So to distinguish whether an expression is a polynomial or not, you need to observe the powers of x present in the expression. So if all the powers of x are whole numbers, then it is a polynomial. If you have negative powers or fractional powers, it is not a polynomial. So if all the coefficients of the polynomial are real, then it is called a real polynomial. If some of them are complex, then it is called a complex polynomial. So the next term that you need to understand is the leading coefficient and the leading term. So if you have a polynomial f of x is equal to an x power n plus an minus 1 x power n minus 1 plus so on a1x plus a0. So we have already seen that this is a polynomial in variable x of degree n if an not equal to 0. The degree of the polynomial is the highest power of x present in the polynomial whose coefficient is non-zero. So if an is non-zero, x power n will be the highest power of x present in this polynomial. Hence, an not equal to 0 implies that this is a polynomial of degree n. Now, what is the leading coefficient? So in this expression, a0, a1, a2, so on, an minus 1 and an are called coefficients of the corresponding powers of x. For example, a0 is the coefficient of x power 0, a1 is the coefficient of x power 1, a2 is the coefficient of x power 2, an minus 1 is the coefficient of x power n minus 1, an is the coefficient of x power n. Now, the leading coefficient is the coefficient of the highest power of x. In this case, an is called the leading coefficient. This an, which is the coefficient corresponding to the highest power of x, is called the leading coefficient. And this whole an with x power n is called the leading term. So an times x power n is called the leading term. So I hope these two are clear. Leading coefficient is the coefficient corresponding to the highest power of x, and the coefficient along with the corresponding power of x is called the leading term. Now, based on the degree of the polynomial, so different polynomials have different names. So let us see the names of the polynomials. So the degrees of polynomial can start from 0. So if the degree is 0, the name of the polynomial is a 0 degree polynomial or a constant polynomial. That means if it does not contain any power of x. So if the polynomial is just a constant, for example, 5 is a polynomial. It does not have any terms consisting of x's. So you can think of 5 as 5 times x power 0. So it contains only 0 power of x. Hence, the degree of this constant polynomial is 0. So whenever you have a constant, it can be thought of as a constant polynomial of degree 0. Now if the degree is 1, it means the highest power of x present is 1. For example, 2x minus 5. This is a polynomial of degree 1 and is also called a linear polynomial. Linear polynomial. Because if you draw the graph of this polynomial, you get a straight line, you get a linear graph. Next, if the degree is 2, for example, if you have x square minus 2x plus 6, so this is a polynomial with degree 2. And this type of polynomial are called quadratic polynomials. Quadratic polynomial. And if the degree is 3, for example, 3x cube minus 5x plus 8. So this is called a cubic polynomial. If the degree is 3, then the polynomial is called a cubic polynomial. If the degree is 4, 5x power 4 minus 2x cube plus 5x square minus 2x plus 7. So this is called a biquadratic polynomial. A polynomial of degree 4 is called a biquadratic polynomial. And the higher degrees of polynomials does not have any special name. So we just call it nth degree polynomial. That is, if a polynomial has a degree 5, we don't have a special name for it. We just call it a 5th degree polynomial, a 6th degree polynomial, a 7th degree polynomial, so on. Next, you have a very special polynomial which is called a 0 polynomial. It's not a 0 degree polynomial. So you have something called a 0 polynomial. So 0 polynomial is nothing but 0. A constant 0 is called a 0 polynomial. And for the constant 0, the degree is not defined. Degree is not defined. So other than 0, if you have any other constant, then it becomes a constant polynomial whose degree is 0. But if you have the number 0, it is called a 0 polynomial and the degree of the polynomial is not defined. So two polynomials are said to be equal if all the corresponding coefficients of like powers of x are equal. If you have a polynomial f of x is equal to a0 plus a1x plus a2x square plus so on up to an x to the power n, and g of x is equal to b0 plus b1x plus b2x square plus so on up to bn x power n. So these two polynomials will be equal. F of x is equal to g of x if and only if the coefficients corresponding to the like powers of x are all equal. That is, a0 is equal to b0 and a1 is equal to b1 and a2 is equal to b2 and so on, an is equal to bn. So if each and every power of the like powers of x, if each and every coefficient of the like powers of x are equal, then only we can say that f of x is equal to g of x. So let us look at what complete and incomplete polynomials are. So if a polynomial contains all the terms corresponding to all the powers of the variable from 0 to n, then it is called a complete polynomial. A complete polynomial is a polynomial which contains all the terms corresponding to all powers of x, to all powers of x from 0 to n is called a complete polynomial. For example, if you have 5x power 4, if you have a 4th degree polynomial, so it should contain all the different powers of x, that is power 4 minus 3x cube plus 2x square plus 6x minus 7. This is an example of a complete polynomial because it contains a constant term, an x term, x square, x cube as well as x power 4 term. If some of the powers of x are missing in between, then it is called an incomplete polynomial. Incomplete polynomial is when some powers of x are missing in the equation, in the expression. That is, if you have 5x power 4 plus 2x square plus 6x minus 7. So this is an incomplete polynomial because x cube term is missing. So if no term is missing, then it is called a complete polynomial. If at least one of the term is missing, then it is called an incomplete polynomial. The first theorem that we are going to look at in the theory of equations is very simple. It states that if f of x is a polynomial of degree m, if f of x is a polynomial of degree m and g of x is a polynomial of degree n. If you have two polynomials, one of degree m and the other of degree n, then f of x into g of x, if you multiply these two polynomials, f of x into g of x is also a polynomial, of degree m plus n. So this is the first theorem, which is very simple to understand. If f of x is a polynomial of degree m and g of x is a polynomial of degree n, then f of x times g of x is a polynomial of degree m plus n. So I'm not going to prove this. This looks like a very obvious theorem. I'll just give you an example of what we are dealing with. So for example, if you have a quadratic 2x square minus 5x plus 6, we have a polynomial of degree 2. And if you have a polynomial of degree 1, x minus 3, this is a polynomial of degree 1. Now if you multiply these two, so you get 2x cube, right? 2x cube minus 5x square minus 6x square, that is minus 11x square. Next, plus 15x plus 6x plus 21 times x minus 18, right? This is a polynomial of degree 3, which is equal to 2 plus 1, So if you have a polynomial of degree m and a polynomial of degree n, then f of x times g of x is a polynomial of degree m plus n. Division algorithm for polynomials states that if f of x and g of x are two polynomials corresponding to f of x and g of x as two polynomials, there exists two polynomials q of x and r of x which are unique. So corresponding to f of x and g of x, there exist two polynomials q of x and r of x which are unique, satisfying f of x is equal to q of x times g of x plus r of x, where r of x is equal to 0 or degree of r of x is less than degree of g of x. This is called the division algorithm. If f of x and g of x are two polynomials, correspond to these two polynomials, there exists two unique polynomials q of x and r of x such that f of x is equal to q of x times g of x plus r of x, where r of x is either equal to 0 or the degree of r of x is less than degree of g of x. And this q of x is called the quotient and this r of x is called the remainder. This algorithm looks complicated, but what it effectively says is, if you have two polynomials f of x and g of x, if you divide f of x by g of x, you know how to divide polynomials, you get some unique quotient and some unique remainder whose degree is less than the degree of g of x, or the remainder can also be equal to 0. For example, if f of x is a polynomial and g of x is a linear polynomial, let us take a particular case. If g of x, that is a divisor polynomial, is a linear polynomial, then what does this theorem say? You have a q of x and r of x such that r of x is either equal to 0 or the degree of r of x is less than the degree of g of x. But g of x degree, so degree of g of x is equal to 1. This implies degree of r of x has to be equal to 0, right? Or r of x has to be 0. That is, the value of remainder if f of x is divided by a linear polynomial is either a constant or a 0. If f of x is divided by a quadratic, then the remainder can be a linear or a constant or a 0. You have three options. If the divisor is a cubic, then the remainder can be quadratic, linear, constant or 0. So this is what division algorithm says. And if on division of f of x by g of x, by chance if you get r of x as equal to 0, if r of x is equal to 0, this implies g of x is a factor of f of x. So we say that g of x is a factor of f of x if the remainder becomes 0. Or I can say that g of x is a factor of f of x, or I can say g of x divides f of x. G of x divides f of x. And I write it like this: g of x, vertical line, f of x. This has to be read as g of x divides f of x. If remainder on division is equal to 0, then we say that g of x is a factor of f of x, or g of x divides f of x. For example, let us take two polynomials. So let us take f of x as 4x power 4 minus 2x cube plus 3x square minus 5x plus 10. And let us take the next polynomial g of x as x square minus 2x plus 6. So corresponding to this f of x and this g of x, what are the polynomials q of x and r of x? So to get that, just need to divide these two polynomials. 2x cube plus 3x square minus 5x plus 10 divided by x square minus 2x plus 6. So I hope you know how to divide polynomials. So first x square into 4x square x square into 4x square is 4x power 4 minus 8x cube plus 24x square. So if you subtract one from the other, this gets cancelled. So minus 2x cube plus 8x cube is 6x cube minus 24x square plus 3x square is minus 21x square minus 5x. And x square times 6x is 6x cube minus 12x square plus 36x minus plus minus. So 12x square minus 21x square is minus 9x square minus 41x plus 10. So x square times minus 9 is equal to minus 9x square plus 18x minus 54 plus minus plus. So 18 minus 41x minus 18x minus 59x plus 54 plus 10 is plus 64. So once you divide f of x by g of x, you get some quotient and you get some remainder. As you can very clearly see, the degree of the remainder is less than the degree of the divisor. So degree of r of x is equal to 1 and degree of g of x is equal to 2. So degree of r of x is less than degree of g of x. R of x is not equal to 0. Hence, g of x does not divide f of x. G of x does not divide f of x. And what is the degree of the quotient? Degree of q of x is nothing but degree of f of x dividend minus degree of g of x. So if you subtract the degree of this, if you subtract the degree of this from the degree of this, so degree of the dividend minus degree of the divisor gives you the degree of the quotient. Because f of x is equal to q of x times g of x plus r of x. So obviously r of x degree is less than g of x degree. Hence q of x into g of x has more degree than r of x. So the effective degree of the whole expression is the degree of this expression. And what is the degree of q of x into g of x? Degree of q plus degree of g. So degree of f of x is equal to degree of q of x plus degree of g of x. Hence the degree of q of x is degree of f of x minus degree of g of x. So from the division algorithm, you can guess the degree of the remainder and you can very easily find the degree of the quotient. The degree of remainder has some options where the degree of remainder has to be less than the degree of the divisor. If the remainder becomes 0, then the divisor is a factor of the dividend. So I hope you have understood the basics of the division algorithm. So let us look at some examples on remainder theorem and factor theorem. So the first example is p of x is a polynomial. I don't know anything about this. The degree is not known. And the information given is that if this polynomial p of x is divided by x minus 1, the remainder is equal to 2. And when this p of x is divided by x minus 2, the remainder is 3. So if this information is known, find the remainder when p of x is divided by x square minus 3x plus 2. That is the product of these two. X minus 1 into x minus 2 is x square minus 3x plus 2. So individually, if you are dividing with the linear factors, the remainders are known. What is the remainder when p of x is divided by this complete factor? So how do we analyze this question? So if p of x is divided by x minus 1, you're given that the remainder is equal to 2. And similarly, if p of x is divided by x minus 2, you're given that the remainder is equal to 3. And you're asked to find the remainder when p of x is divided by x square minus 3x plus 2. So we don't know the remainder in this case. So let us assume that the remainder is ax plus b. So why am I assuming this as ax plus b? Because by applying division algorithm, we know that the degree of remainder should be less than the degree of the divisor. The degree of divisor is 2. Hence, the degree of remainder can at most go to 1. It can also be 0. When you create equations, if you solve the equations, if you get a is equal to 0, then the remainder might be a constant. If b is also equal to 0, the remainder might be 0 also. Now, let us try to create some equations to find ax plus b. Now, according to the first equation, p of x when divided by x minus 1, remainder is equal to 2. So, what is the remainder using remainder theorem? When p of x is divided by x minus 1, the remainder is p of 1, right? And this is given as 2. And from this condition, the remainder which is p of 2 is given as 3. These are the two informations now. And next, from this, if the quotient is some q of x, so can I write p of x as x square minus 3x plus 2 times q of x plus the remainder ax plus b. Dividend is equal to divisor into quotient plus remainder. Now from this equation, can I find the values of a and b using this information? That's the question. So if this polynomial is equal to this polynomial, for every value of x, both sides should give you the same answer. Then only we say that these two are equal. So let us take a special case and put x is equal to 1. So for x is equal to 1, p of 1 is equal to 1 minus 3 plus 2 is 0. 0 times q of x is 0 plus a into 1 plus b. So p of 1 is equal to a plus b. And what is p of 1 given as 2? This implies a plus b is equal to 2. This is the first equation. Now for x is equal to 2, what happens? For x is equal to 2. So p of 2 is equal to, so when you put 2 in the place of x, 4 minus 6 plus 2 is again equal to 0 plus 2a plus b. This implies 2a plus b is equal to p of 2, which is given as 3. So you have two equations. You just need to solve these two equations. So if you subtract one from the other, you get a is equal to 1 and b is equal to 1. Now you got the values of a and b, hence the required remainder is x plus 1. So in this question, you're given that p of x is the polynomial x cube minus 3x square plus 2x plus 5. And q of x is 2x4 minus 3x2 plus 1 plus b. And the condition given is that both give the same remainder when divided by x plus 1. If that is so, find the value of b. If you're given one piece of information, you're asked to find one number. So from the information, try to create an equation and solve that. So what does remainder theorem say? When p of x is divided by x plus 1, the remainder is p of minus 1, right? When q of x is divided by x plus 1, the remainder is q of minus 1. According to the given information, both give the same remainder. That means these two are equal. So this implies p of x is this. What is p of minus 1? You just need to put minus 1 in the place of x. So minus 1 whole cube is minus 1. Minus 3 times 1 minus 3 plus 2 times minus 1 is minus 2 plus 5 is equal to. Here also you just need to put minus 1 in the place of x. So you get 2 minus 3 plus b. So this implies 5 and minus 5 are getting cancelled. Minus 1 is equal to minus 1 plus b. And this implies b is equal to 0. That means for this condition to be valid, the value of b has to be equal to 0. So in this example, you're given that p of x when divided by x square minus 5x plus 6 leaves remainder 2x plus 7. If that is so, you're asked to find the reminders when this same p of x is divided by x minus 2 and x minus 3. As you can very clearly see, this x minus 2 and x minus 3 are the factors of this. So how do we analyze this? So we cannot use our factorization theorem in the first step because the divisor is not a linear factor. So according to the first information, if p of x is divided by x square minus 5x plus 6, the remainder is found out to be 2x plus 7. Assume that you got some quotient q of x. So from division algorithm, you can write that p of x is equal to x square minus 5x plus 6 times q of x plus 2x plus 7. Now, you're asked to find the reminders when p of x is divided by x minus 2 and x minus 3. That means effectively you're asked to find p of 2 and p of 3. These are to be found, right? How do you find p of 2? Simply by putting x is equal to 2. So what is p of 2? So if you are putting x is equal to 2 here, because x minus 2 is a factor of this whole part becomes 0. Because 4 plus 6 minus 10 is 0. So this part becomes 0. So 0 plus 2 into 2 is 4 plus 7 is 11. So p of 2 is equal to 11. That means the remainder when x minus 2, the function p of x is divided by x minus 2 is 11. Similarly, what is p of 3? So again, correspond to 3 also, you get this as 0. 9 plus 6, 15 minus 15. So this becomes 0 again. You just need to put x is equal to 3 here. 6 plus 7. 6 plus 7 is equal to 13. So the remainder when p of x is divided by x minus 3 is equal to 13. So in this example, you're asked to find the remainder when x power 999 is divided by x square minus 4x plus 3. So x power 999 is divided by x square minus 4x plus 3. So you get some quotient and you get some remainder. So what is the form in which remainder might look like? This is a quadratic function. The degree of remainder is less than the degree of the divisor. So the remainder should be of the form ax plus b. So let me assume that the remainder is of the form ax plus b. So I just need to find a and b to get the value of the remainder. So using the division algorithm, I write that the dividend is equal to divisor into quotient plus remainder ax plus b. So now to find ax plus b, you try to form two equations in a and b and try to solve it. So how do you form the two equations? So we take some special numbers. So the numbers are nothing but the factors of this polynomial. We know that x square minus 4x plus 3 can be factorized as x minus 1 times x minus 3. That means at x is equal to 1 and x is equal to 3, this expression becomes 0. So let us use that property. For x is equal to 1, what does this equation become? 1 power 999 is 1 is equal to, so this becomes 0. 0 times q of x is 0. a times 1 plus b. That means a plus b is equal to 1. Next, for x is equal to 3. For x is equal to 3, what happens? 3 power 999 is equal to. So for x is equal to 3, also this expression becomes 0. 9 plus 3 is 12, minus 12 is 0. So this whole expression vanishes. So you just have this expression. So x is equal to 3. So 3a plus b. Now you have two equations in a and b. You just need to solve them. So subtract one from the other. So 2a is equal to 3 power 999 minus 1. This implies a is equal to 3 power 999 minus 1 by 2. 3 power 999 minus 1 by 2. So you get the value of a. So what is the value of b? b is equal to 1 minus a. So b is equal to 1 minus of 3 power 999 minus 1 by 2. That is equal to, so 2 plus 1. 3 minus 3 power 999 by 2. So this will be the value of b. This will be the value of a. So the remainder, the required remainder is nothing but 3 power 999 minus 1 by 2 times x plus 3 minus 3 power 999 by 2. So in this example, you're given that f of x is a 4th degree polynomial, and when f of x is divided by x plus 6, the quotient is q of x and the remainder is minus 6. And when the same f of x is divided by q of x plus 1, the quotient is x plus 6 this time, and you're asked to find the remainder. You're asked to find this. So let us try to create the equations and try to solve them. So from the first information, f of x can be written as q of x times x plus 6, q of x times x plus 6 minus 6. Dividend is equal to divisor into quotient plus remainder. And from the second information, you can write f of x as q of x plus 1 times x plus 6 plus r of x. So from these two conditions, can you get some useful conclusions? You also have another information, which is f of x is a 4th degree polynomial. Now from this equation, q of x times x plus 6, q of x times x plus 6 is nothing but f of x plus 6. And from this, f of x is equal to q of x times x plus 6 plus x plus 6 plus r of x. Now q of x into x plus 6 is nothing but f of x plus 6. So let us substitute that. So f of x plus 6. Now this f of x and this f of x gets cancelled. This implies r of x is equal to x plus 12 on the negative side, minus of x plus 12. So that's the required remainder, minus of x plus 12. So in this example, you're given that f of x is a cubic polynomial, and you're given 4 informations. When divided by x plus 3 and x plus 4, the remainders are zeros. And when divided by x plus 5, the remainder is 4. X plus 6, the remainder is 6. So if that is so, what is the remainder when f of x is divided by x plus 7? So how can we use these informations to get the answer? So f of x is a cubic polynomial, and when divided by x plus 3 and x plus 4, the remainders are zeros. That means x plus 3 and x plus 4 are factors of p of x, or factors of f of x. So can I write f of x as x plus 3 times x plus 4 times, what is the other factor? So I know that x plus 3 and x plus 4 are 2 factors, and f of x is a cubic polynomial. So what will be the quotient that is remaining here? The quotient has to be a linear, right? Because already the quadratic has been covered. So let us assume that the remaining factor is of the form ax plus b. So I'm assuming f of x to be x plus 3 times x plus 4 times ax plus b. Now I am having two unknowns. If I can find two equations and solve them, I can get these numbers. So two informations are left now. So first, x plus 5, the remainder when f of x is divided by x plus 5 is nothing but f of minus 5. So let us put x is equal to minus 5. So f of minus 5 is equal to minus 5 plus 3 is minus 2, minus 5 plus 4 is minus 1 into minus 5a plus b. And f of minus 5 is given as 4. So this is equal to 4. So minus into minus gets cancelled, 2 gets cancelled 2 times. This implies minus 5a plus b is equal to 2. Next, let us go to this equation. When x is equal to minus 6, so f of minus 6, which is equal to 6, can be written as minus 6 plus 3 is minus 3, minus 6 plus 4 is minus 2 times minus 6a plus b. This implies this minus and minus gets cancelled. 3 2s are 6 and 6 gets cancelled. Minus 6a plus b is equal to 1. So you got two equations. Just try to solve them. Subtract one from the other. So a is equal to 1 and b is equal to 2 plus 5, which is equal to 7. So minus 5 plus 7 is 2, minus 6 plus 7 is 1. Hence f of x is equal to x plus 3 times x plus 4 times 1 and 7. Just need to put them x plus 7. Now if you're asked to find the remainder when f of x is divided by x plus 7. So as you can very clearly see, x plus 7 is a factor of f of x. Hence the remainder which is equal to f of minus 7 will be equal to 0. So in this question, you're asked to factorize the polynomial x power 4 minus 10x square plus 9. So this is a 4th degree polynomial. There is no direct way in which you can solve this. So usually what we do here is we take trial and error and try to find some of the solutions using factor theorem. So if p of x is equal to x power 4 minus 10x square plus 9. So whenever you have a polynomial which is of a degree more than 2, so you try to find some of the solutions, some of the factors by using trial and error. So first let us put x is equal to 1. So one of the things that you observe here is the sum of all the coefficients is equal to 0. 1 minus 10 plus 9. Sum of all the coefficients is equal to 0. And we have seen from the corollary that x minus 1 will be a factor in that cases. So p of 1 is equal to 1 minus 10 plus 9, which is equal to 0. This implies x minus 1 is a factor. And p of minus 1, if you put x is equal to minus 1, you can see that you get 1 minus 10 plus 9 again, which is equal to 0. This implies x plus 1 is also a factor. So out of 4 factors, you got 2 factors already. So the remaining 2 factors can be very easily found out. So first what we do is we divide the expression with these 2 factors to get the remaining factor. So if you divide x power 4 minus 10x square plus 9, so you can divide first by x minus 1 and then the quotient which is obtained by x plus 1, or you can directly divide by x square minus 1 because this is a complete factor. So let us divide with x square minus 1. So you get x square, sir. X square x power 4 minus x square minus plus, so minus 9x square plus 9. So minus 9s are minus 9x square plus 9. So gets cancelled, is equal to 0. This implies my p of x is equal to x square minus 1 times x square minus 9. So this quadratic factor is very easy to simplify, very easy to factorize. This is nothing but x plus 3 into x minus 3. That is equal to x plus 1 times x minus 1 into x plus 3 times x minus 3. So what is the basic process here? Whenever you're given a polynomial which is of a degree greater than 2, so we try to get sum of the factors using trial and error and factor theorem. So once you get sum of the factors, until only a quadratic is left, and for the final quadratic we can solve the equation and get the factors. So in this video, let us look at a very interesting technique of polynomial division called Horner's synthetic division. So you know how to divide two polynomials. Let us take an example. So if you're asked to divide x cube minus 5x square plus 2x plus 7 by x plus 1. So how do you do this division? So the process that you usually do is x plus 1, x cube minus 5x square plus 2x plus 7. So x into x square is x cube, right? X into what is x cube? X into x square is x cube, and 1 into x square is x square. You subtract one from the other, x cube gets cancelled. So minus 5x square minus x square is minus 6x square, and you borrow one term. Now x into how much is minus 6x square? X into minus 6x is minus 6x square. So you write minus 6x square, and 1 into minus 6x is minus 6x. So you subtract one from the other. So minus 6x square and plus 6x square will get cancelled. So plus 2x minus of minus 6x is plus 6x. So you have 8x plus 7. Now x into what is 8x? 8 is 8x. 1 into 8 is 8. So if you subtract these two, you get minus 1. So when you divide this polynomial by x plus 1, the quotient is x square minus 6x plus 8, and the remainder is minus 1. And the remainder can be directly found out by putting x is equal to minus 1 in this expression. So let us check whether the remainder theorem is working. So if this polynomial is p of x, so what is p of minus 1? Minus 1 minus 5 minus 2 plus 7, which is equal to minus 1. So the remainder theorem is valid. Now this is the way in which you do the general division. So now there is an easy way to do this, and the method is called Horner's synthetic division. So now let us try to do this division using Horner's synthetic division. So there are several levels of simplifications that you can do in Horner's synthetic division. The first type of simplification that we do is by avoiding writing the coefficients of x's. For example, if you want to divide this by this, I just write the coefficients of different powers of x. 1, minus 5, 2, 7. This is the dividend, and the divisor is x plus 1. Here also the coefficient of x is 1 and the next coefficient is also 1. Now we just need to divide these numbers by these numbers. We use exactly the same process. So 1, this is the leading coefficient here, this is the leading coefficient here. So 1 into 1s are 1, and 1 into 1s are 1. So you subtract one from the other, ones will get cancelled. Minus 5 minus 1 is minus 6, and you borrow this 2. Next, Now the leading coefficient is again 1 here. The leading coefficient is minus 6 here. So 1 times minus 6 is equal to minus 6. 1 times minus 6 again is minus 6. So you subtract again. Minus 6 and plus 6 gets cancelled. So 2 plus 6 is 8. And you borrow the next number here. Again 1 8s are 8 and 1 8s are 8 again. You subtract one from the other. So 8 and minus 8 gets cancelled. 7 minus 8 is minus 1. So the whole division process is complete. And you can see that the division process is complete when the number of numbers that you have in the divisor and the number of numbers you have in the remainder becomes less than the number of numbers in the divisor. So the divisor has 2 coefficients. The remainder should have at most 1 coefficient. So now once you have these numbers, at last you can back convert these into polynomials. So this corresponds to, there are 3 numbers. So this corresponds to the constant term, this to the x term, this to the x square term. It is x square minus 6x plus 8. That is the quotient. And what is the remainder? You have only single term. So the remainder is a constant which is minus 1. So you can see that you get the exact same answers from the Horner's synthetic division also. And simplification being that you don't need to write different powers of x. So let us look at the next level of simplification in Horner's process. We are going to solve the same question by a further simplified process. Here, what we do is, we take the leading coefficient of divisor as it is, but we change the signs of all the remaining coefficients. So the leading coefficient 1 is written as 1, but all the remaining coefficients will have the signs changed. That is, instead of plus 1, we write minus 1 here. So what is the simplification that we get by following this process? So instead of the subtraction process, the processes convert to addition process, which are simple. So now 1 ones are 1 and minus 1 into minus 1 is minus 1. Now you don't need to bother about the first subtraction. So just at each stage start leaving one of the column and go to the next columns. So now minus 5 minus 1 is minus 6. Already we have changed the sign here. So instead of subtraction we can do addition now. Minus 6 and 2. So 1 minus 6 are minus 6 and minus 1 into minus 6 is plus 6. So you can leave the first column. Go to the next column. 2 plus 6 is 8. Next number is 7. So 1 8s are 8 and minus 8. So leave this column. 7 minus 8 is minus 1. So if you change the coefficients, all of them except the leading coefficients, and at each stage you leave one of the column, and you can convert the subtraction process into addition process. So I hope this is very straightforward. So the quotient is again x square minus 6x plus 8 and the remainder is equal to 1. So here we are doing it stage by stage. Next you have a further simplification where you can get all the answers in a single line. Let us see that process. So the final level of simplification when you want to divide a polynomial with a linear polynomial is that we stop taking the leading coefficient. We just ignore the leading coefficient. We don't write it and just change the sign of the constant term. So if you want to divide by x plus 1, just write minus 1 here. So now, in the first stage, get this 1 here. So we'll just carry over the leading coefficient here, 1. And 1 into minus 1 is minus 1. And minus 5 minus 1, you add these two, you get minus 6 as the answer. And minus 6 into minus 1 is plus 6. And you add these two, you get 8 as the answer. 8 into minus 1 is minus 8. So 7 minus 8 is minus 1. So the last digit is the remainder and the remaining digits correspond to the quotient. Hence, the quotient is x square minus 6x plus 8 and the remainder is equal to minus 1. So in this process, if you want to divide any polynomial by a linear polynomial, you can directly do it in one step if the leading coefficient is equal to 1. So let us do some more examples in the final process. So now let us try to divide the same polynomial by x minus 3. So how do we do it? Using Horner synthetic division. So you just write the coefficients corresponding to the dividend, and correspond to x minus 3, I am ignoring the leading coefficient and I am changing the sign of the constant term. So you have to take 3 here. Now let us start our division. So I'll just carry over this 1 in the starting 1. Now 1 into 3 is 3. So minus 5 plus 3 is minus 2. And minus 2 into 3 is minus 6. 2 minus 6 is minus 4. And minus 4 into 3 is minus 12. And 7 minus 12 is minus 5. And this digit corresponds to the remainder. This corresponds to the quotient. Hence the quotient is x square minus 2x minus 4 and the remainder is equal to minus 5. So this is how we divide any given polynomial by a linear polynomial. So let us take this example. You are asked to divide x power 7 minus 5x power 5 plus 6x4 minus 2x2 plus 5x minus 6 by x minus 2. So let us use synthetic division. So to do that, first let me write all the coefficients correspond to the dividend. So 1, x power 7 coefficient is 1. So you cannot directly write all these numbers. You have to write coefficient by coefficient corresponding to each power of x. X power 7 coefficient is 1. What is x power 6 coefficient? X power 6 is not there, so x power 6 coefficient is 0. X power 5 coefficient is minus 5. X power 4 coefficient is 6. X cube coefficient is missing, so it is 0. X square coefficient is minus 2. X coefficient is 5 and constant is minus 6. So you have a total of 8 terms. Now I want to divide this by x minus 2. So I just need to write 2 here, right? So now let us start our division process. So let us carry this 1 directly. So now 1 2s are 2 and the sum is 2. 2 2s are 4. The sum is minus 1. Minus 1 into 2 is minus 2. 6 minus 2 is 4. 4 2s are 8. 0 plus 8 is 8. 8 2s are 8. 2s are 16. 16 minus 2 is 14. 14 2s are 28. 28 plus 5 is 33. 33 into 2 is 66. 66 minus 6 is 60. So the last number corresponds to the remainder. All these numbers correspond to the quotient. So the quotient has 7 terms. It is a 6th degree polynomial. So q of x is equal to x to the power 6 plus 2x to the power 5 minus x to the power 4 plus 4x cube plus 8x square plus 14x plus 33. And the remainder is equal to 60. So this is how you divide any polynomial by a linear polynomial if the leading coefficient is 1. So let us see what to do if the leading coefficient is not equal to 1. So let us say that you are asked to divide 6x cube plus 8x square minus 2x plus 7 by the polynomial 2x minus 3. Here you can see that the leading coefficient is not equal to 1. So I cannot ignore this coefficient. So how do we do this? Using Horner synthetic division. So the coefficients again are 6, 8, minus 2 and 7. And now what you do is to remind you that the coefficient of the leading power of x is 2, I write a 2, and all the remaining coefficients I change the sign. That is, if you have minus 3, I take it as plus 3. So this is the leading coefficient, this is the constant term. So now what you do is, at each stage, whatever is to be carried down, you have to divide it by the leading coefficient. So that's a simple theory. So whatever number is to be carried down, you have to divide that number by the leading coefficient at each step. So you remember that and go forward. So normally if you have 1 here, you directly carry the 6 downwards. So now you cannot carry 6 completely. What you need to do is 6 by 2. You divide by 2 and get 3 down. Now 3 into 3 is 9. Now 8 plus 9 is 17. 8 plus 9 is 17. But I write 17 if the leading coefficient is 1. If the leading coefficient is 2, so we write 17 by 2. So the number here is 17 by 2. Now 17 by 2 into 3. 17 by 2 into 3. So 51 by 2. 51 by 2. Now add these two. So minus 2 plus 51 by 2. So 51 minus 4, that is 47 by 2. So the addition of these two is 47 by 2. But you cannot write 47 by 2 here. You have to divide it with 2. So you have 47 by 4 here. Now 3 into 47 by 4. 3 into 47 by 4. 120 plus 21. 141 by 4. 141 by 4. And in the remainder part, you can directly write the answer. So till you are dealing with the quotient, you need to divide with 2. So now what is the remainder? 7 plus 141 by 4. That is 28 plus 141. 169 by 4. So in the remainder, obviously you don't need to divide with the leading coefficient because the division is complete. So the quotient is 3x square plus 17 by 2 times x plus 47 by 4. This is the quotient and the remainder is 169 by 4. Again, I want to check whether the remainder theorem is valid or not. So if you divide this by 2x minus 3, the remainder is nothing but p of 3 by 2, right? So you just put 3 by 2 in the place of x. So 6 times 27 by 8. 6 times 27 by 8 plus 8 times 9 by 4 minus 2 times 3 by 2 is 3 plus 7. So 2 3s are 2 4s are. So you have 27 into 3, 60 plus 21, 81 by 4 plus 9 8s are 72 by 4 plus 4. That is equal to 81 plus 72 is 153 by 4 plus 4, which is equal to 153 plus 16, 169 by 4. So you're getting the same remainder. And this is the quotient. So I hope you understand how to do the division if the leading coefficient is not 1. So at each stage, whatever is the answer that you are getting, you have to divide it by the leading coefficient and then follow the same process. So in one line you get the answer. So now let us see how to divide polynomial by polynomial if the divisor is not a linear polynomial. If it is a higher degree polynomial, let us see how to do it. So let us do this division by all the three processes. First by direct division, next by Horner's division of first simplification and Horner's division of second simplification. First, 2x power 4 minus 5x cube plus 3x square minus 7x plus 8 divided by x square minus 5x plus 2. So x square into 2x squares are 2x power 4 minus 10x cube plus 4x square. Subtract 10x cube minus 5x cube is 5x cube. 3x square minus 4x square is minus x square, and you borrow the next term, minus 7x. Now x square into what is 5x cube? X square into 5x is 5x cube minus 5x into 5x is minus 25x square plus 10x minus plus minus. So this 2 gets cancelled. 25x square minus x square is 24x square minus 17x, and you borrow this 8. So x square into 24s are 24x square minus 120x. 2 into 24 is 48 minus plus minus 24x square gets cancelled. 120 minus 17, 103x minus 40. So now the division is complete. The divisor is a quadratic, the remainder is a linear, and this is the quotient and this is the remainder. So next, let us use Horner synthetic division of type 1. So here I'll write all the coefficients: 2, minus 5, 3, minus 7 and 8. So these are the coefficients of the dividend, and the coefficients of divisor are 1, minus 5, 2, and I follow the same process. 2s are, so 1 2s are 2, minus 10 and 4. So if you subtract these 2 and 2 gets cancelled. 10 minus 5 is 5, 3 minus 4 is minus 1. You borrow the next term. Next, the leading coefficient is 1 here and 5 here. 1 5s are 5, and minus 5 into 5 is minus 25. 2 into 5 is 10. So if you subtract 5 and minus 5 gets cancelled. So minus 1 plus 25 is 24. Minus 7 minus 10 is minus 17 and 8. So as you can very clearly see, the numbers that you're getting in normal division are exactly same as the numbers you're getting here. So 124s are 24, minus 5 into 24 is minus 120, 2 into 24 is 48. Subtract again, 24 minus 24 gets cancelled. So 120 minus 17 is 103. 8 minus 48 is minus 40. So you have 3 terms here, you have 2 terms here. That means the degree of remainder has gone smaller than the degree of divisor, hence our division process is complete. So the quotient corresponds to the numbers 2, 5, 24. That is 2x square plus 5x plus 24. And the remainder is having 2 terms. Minus 40 is the constant term. 103 corresponds to the x term. So 103x minus 40 exactly same as this. Now if you use a better Horner's process, so what you need to do is, so 2 minus 5, 3 minus 7, 8. So what you do is write the leading, if the leading coefficient is 1, you don't need to write it. Just change the signs of the remaining powers of x. So you have plus 5 and minus 2, plus 5 and minus 2. So start doing your process. So first send this 2 down. Now 5 2s are 10 and 2 minus 2s are minus 4. Now minus 5 plus 10 is plus 5. Now use this 5 and write the terms. 5 5s are 25 and 5 minus 2s are minus 10. So 25 plus 3 is 28, minus 4 is 24. Now use 24 with 5. 24 into 5 is 120 and 24 into minus 2 is minus 48. So minus 7 minus 10 is minus 113 plus 120 is 103. 8 minus 48 is minus 40. So you have two terms here. So just the last two terms goes to the remainder. First three terms goes to the quotient. As the quotient is 2x square plus 5x plus 24. The remainder is 103x minus 40. I hope you can see that this process is easier than the remaining two processes. Now let us take some more examples and directly practice this method. So in this question, you're asked to divide 3x to the power 5 plus 6x square plus 5x minus 2 with x cube minus 2x square plus 5. So we'll directly use the shortest horns process. So first let us write all the coefficients. X power 5 quotient is 3. X power 4 is missing, so the coefficient is 0. X cube is missing, so the coefficient is 0. X square is 6. X 5 and the constant is minus 2. And let us write the numbers correspond to the divisor. The leading coefficient is 1, so I don't need to write it. And all the other coefficients, just change the sign and write. So you have minus 2x square, you write plus 2. X coefficient is 0, so you write 0. The constant term is plus 5, so just write minus 5. Now let us start our division process. So because the leading coefficient is 1, just get whatever number is here down. So 3. Now multiply this with all the three numbers. 3 2s are 6, 3 zeros are 0, 3 minus 5s are minus 50. Now 0 plus 6 is 6. Now use the 6 and multiply all this. 6 2s are 12, 6 zeros are 0, 6 minus 5s are minus 30. Now add all this. 0 plus 0 plus 12 is 12. Now using this 12, do the multiplication. 12 2s are 24, 12 zeros are 0, 12 minus 5s are minus 60. So hence the division process is done. Once you reach to the last column, the division process is done. Now add all this. 24 plus 6 is 30, minus 15 is 15. Next, 5 minus 30 is minus 25, and minus 2 minus 60. Minus 2 minus 60 is minus 62. Now as you can see, you are dividing a fifth degree with a cubic equation. You are dividing a fifth degree with a cubic equation. So what is the degree of the quotient? The degree of the quotient is a quadratic, right? That means you should have three numbers. So the first three numbers correspond to the quotient and the next three numbers correspond to the remainder. So the other way of trying to understand this is whatever are the number of numbers that are there here, those many numbers goes to the remainder. If you have a linear factor, you have only one number here, so only one number goes to the remainder. If you have a quadratic, you get two numbers here, so two numbers are there in the remainder. Three numbers. So the quotient is nothing but 3x square plus 6x plus 12, and the remainder is nothing but 15x square minus 25x minus 62. So I can write the polynomial as divisor into this plus this. So I hope the process is clear. So let us take a similar example. So you're asked to divide the same expression, this time with x square plus 4x minus 2. So how do we do this? Again, write the coefficients 3, 0, 0, 6, 5, minus 2. Now the leading coefficient is 1, so I don't need to write it. So change the signs of the remaining coefficients. So you get minus 4 and plus 2. So let us start our division. So first, just bring this 3 down, and now use this 3 as a multiplying factor for these two numbers. Minus 12 3 2s are 6. So 0 minus 12 is minus 12. And minus 12 into minus 4 is 48. Minus 12 into 2 is minus 24. If you add these two, 48 plus 6 is 54. 48 plus 6 is 54. Now 54 into minus 4, minus 216. 54 into 2 is 108. 54 into minus 4 is minus 216. 54 into 2 is 108. Now add all this. So 200 minus 240 plus 6 minus 234. Minus 234. Now minus 234 into minus 4. So 800 plus 120, 920 plus 16 is 936. And minus 234 into 2 is minus 468. Minus 468. Now the division process is complete. So just add these three. 936 plus 108 is 1044 plus 5, 1049. And minus 468 minus 2 is minus 470. So you have two numbers here. So the last two numbers goes to the remainder and the first four numbers goes to the quotient. Hence the quotient is 3x cube minus 12x square plus 54x minus 234, and the remainder is 1049x minus 470. Again, I hope this is clear to you. Now let us take another example where you have a leading coefficient other than 1. So now let us try to divide 3x power 4 plus 6x square plus 9x minus 1 with 3x square plus 4x minus 3. In this question, the difference is that the leading coefficient of divisor is not equal to 1. So let us start our division. The coefficients of the dividend are 3, x cube coefficient is 0, x square 6, 9 and minus 1. And the divisor has a leading coefficient of 3. So I write this 3. I write this 3 separately. And all the remaining coefficients, I change this sign. So my plus 4 becomes minus 4 and minus 3 becomes plus 3. So let us start our division process. What you need to remember is at each stage, whatever is the number that comes here has to be divided by the leading coefficient. So now if the leading coefficient is 1, 3 would have come down. So now 3 by 3, 1 comes down. Now using 1, do the multiplication. So you get minus 4 and 3. Now you have certain difficulties. You come across fractions now. Now if you have 0 minus 4, if the leading coefficient was 1, you would have got minus 4 down. But this time you have to get minus 4 by 3. Now using minus 4 by 3, do the multiplication. So minus 4 by 3 into minus 4 is 16 by 3. Minus 4 by 3 into 3 is minus 4. Now what is the number that you get here? 9 plus 16 by 3. So 27 plus 16, 37, 43. So 43 by 3. So the number that would come here is 27 plus 16 by 3, that is 43 by 3. So 43 by 3. So if the leading coefficient is 1, I would have got 43 by 3 here. But the leading coefficient is 3. I need to divide this by 3. So 43 by 9. Now we have come to the final stages. 43 by 9 into minus 4. Minus 160 plus 12. Minus 172 by 9. And 3 into 43 by 9 is 43 by 3. So now we have two terms here. We have come to the last two terms. So this is the remainder term. So when you're calculating the remainder term, you don't need to divide by 3. So till the division is going on, you have to go on divide by 3. So now what is the remainder part? 9 minus 4 is 5 minus 172 by 9. 5 minus 172 by 9. So 45 minus 172. So 172 minus 45. 122 plus 5 is 127. So minus 127 by 9. And 43 by 3 minus 1 is 40 by 3. So these two terms correspond to the remainder term. These three terms correspond to the quotient. So quotient is equal to x square minus 4 by 3x plus 43 by 9. And the remainder is minus 127 by 9x plus 40 by 3. So I hope the process is getting clearer to you. Now you can use this Horner synthetic division as a shortcut to do your division process in different questions. So in this video, let us look at the theorems that we have regarding the number of roots of a polynomial equation. So if you have a polynomial equation of the form f of x is equal to 0. So whenever you write a polynomial is equal to 0, this becomes a polynomial equation. So if you have a polynomial equation, a number alpha is called a root of this equation. A number alpha is called a root of this equation if and only if f of alpha is equal to 0. So if you put alpha in the place of x in the polynomial, and if you get 0 as the answer, then we say that this number alpha is the root of this equation. For example, if you have x square minus 5x plus 6 is equal to 0, let us consider this as my f of x. Now, what is f of 2? F of 2 is equal to 4 minus 10 plus 6 is equal to 0, right? So f of 2 is equal to 0. This implies 2 is a root of this equation. So this works in both the ways. F of x is equal to 0. Alpha is called a root if f of alpha is equal to 0. And if f of alpha is equal to 0, then alpha is called a root. So this is the meaning of the root of an equation. So what is another interpretation of the root? So f of x is equal to 0 has alpha as a root. F of x is equal to 0 has alpha as a root if x minus alpha divides f of x. Can I say this? Yes, from remainder theorem and factorization theorem. So if f of x is equal to 0 has alpha as a root, by definition f of alpha is equal to 0, and if f of alpha is equal to 0, from factor theorem x minus alpha has to be a factor of f of x. So these are two ways in which we can determine whether a number is a root of the equation. So now that we have understood the meaning of root of a polynomial equation, let us look at what repeated roots are. So you come across this word often, repeated roots, and the corresponding concept is multiplicity of roots. So let us see what this is. For example, if you have a polynomial f of x, if f of alpha is equal to 0, then I can say that x minus alpha is a factor of f of x. X minus alpha is a factor of f of x. Now, there might be some situations where f of x will be divisible by x minus alpha whole square also. There might be some situations where f of x is divisible by x minus alpha whole square. For example, if f of x is equal to x minus 2 whole square times x minus 3. X minus 2 whole square times x minus 3. Here x minus 3 is a factor and x minus 2 is also a factor and x minus 2 whole square is also a factor. Now in this situation we say that 2 is a repeated root. We say that 2 is a repeated root with multiplicity 2. With multiplicity 2. And if you have another example, f of x is equal to x minus 2 whole cube times x minus 3 whole square times x minus 4. So in this case we say that x minus 2 is a factor of multiplicity 3 and 2 is a repeated root with multiplicity of 3 and 3 is a repeated root with multiplicity of 2 and 4 is not a repeated root, or we can say that 4 is a root with multiplicity of 1. So now I hope you understand what repeated root is and what the multiplicity of a repeated root is. So the multiplicity of a repeated root is more than 1. For a general root, the multiplicity is 1. For a repeated root, the multiplicity is more than 1. So if I have to give it a definition, alpha is called a root of f of x with multiplicity r. Multiplicity r if x minus alpha whole power r divides f of x and x minus alpha whole power r plus 1 does not divide f of x. So I am looking for the maximum multiplicity. Alpha is called a multiplicity of 2. For example, alpha 2 is called a root with a multiplicity 2 if x minus 2 whole square is x minus 2 whole square divides f of x and x minus 2 whole cube does not divide fx. Because if x minus 2 whole cube also divides fx, then the multiplicity will be r plus 1. So if the multiplicity is r, multiplicity is a unique number. So if the multiplicity is r, x minus alpha whole power r should be divisible by f of x, divides f of x, and the next power should not divide f of x. Then we say that alpha is a repeated root with multiplicity r. So once we understand the concept of roots, the fundamental theorem of algebra says that a polynomial equation of degree n has exactly n roots in the set of complex numbers. So every polynomial equation of degree n has exactly n roots in the set of complex numbers. So when I talk about roots, a root of multiplicity 2 has to be taken as two different roots. That is, if f of x is equal to x minus 2 whole square into x minus 3, clearly we can see that this is a cubic equation. So what are the roots of this equation? The roots of this equation are 2, 2 and 3. Because 2 is a repeated root, you have to take it as 2 times. So 2, 2 and 3, you have a total of 3 roots. So every polynomial of degree n has exactly n roots and no more. And no more. That means f of alpha will be equal to 0 only n times and not more than that. If someone claims that, if in a problem it is claimed that a polynomial equation has more than n roots, then there is only one option, then it becomes an identity. That is, all the coefficients have to be 0. All the coefficients has to be 0. So if a polynomial equation of a degree n has more than n roots, if it is claimed that it has more than n roots, then there is only one option: all the coefficients have to be equal to 0. For example, if some coefficient times x square plus some coefficient times x plus some coefficient is equal to 0 has 3 roots. So if someone claims that it has 3 roots, it means for 3 different numbers, if this equation is getting satisfied, for 3 different numbers, if this equation is getting satisfied, then there is only one option: this has to be equal to 0, this also has to be equal to 0, this also has to be equal to 0. Then this becomes an identity. It means for whatever value of x, this equation is valid. So for any polynomial equation with whose coefficients are not all 0, there are exactly n roots correspond to a degree n. This is called the fundamental theorem of algebra and the most important theorem. So we have a theorem called conjugate pair theorem, which states that if a polynomial equation has all of its coefficients as real numbers, that is a polynomial equation with real coefficients. So if you consider a polynomial equation with real coefficients, the non-real complex roots of this polynomial equation always occurs in conjugate pairs. The non-real complex roots always occur in conjugate pairs. For example, if you have a polynomial equation p of x is equal to 0, if it is given that 2 plus 3i is a root of p of x, so I'm assuming that p of x is made up of all real coefficients. That's an important catch which you need to remember. So if p of x is a polynomial equation with all real coefficients, then if 2 plus 3i is a root of p of x, then its conjugate 2 minus 3i will automatically become a root of p of x. If 2 plus 3i is a root of p of x, then 2 minus 3i will automatically become a root of p of x. The non-real complex roots always occur in conjugate pairs. This is one of the theorem that we have. And a similar theorem is if you have a polynomial equation with all rational coefficients, then the non-rational real roots, non-rational is irrational real roots, always occur in conjugate pairs again. Always occur in conjugate pairs. For example, if you have a polynomial p of x is equal to 0, has 2 plus root 3 as a root. So if p of x is equal to 0, where all the coefficients of p of x are rational, this time you should not have any irrational coefficients. If the coefficients are all rational, and if 2 plus root 3, an irrational root, is a root of this equation, then its conjugate 2 minus root 3 will automatically be a root, and 2 minus root 3 is also a root of p of x. So if the coefficients are all rational, then irrational roots always occur in conjugate pairs. If the coefficients are all real, the non-real complex roots always occur in conjugate pairs. Now using this, we can derive an interesting corollary. So the corollary is that every real polynomial equation, that is a polynomial equation with real coefficients of odd degree, has at least one real solution. So all the roots of an odd degree cannot be non-real complex, because non-real complex roots always occur in pairs. So if you take all the non-real complex roots, they'll always be of an even number. So if you have an odd degree equation, we know that a polynomial equation of degree n has exactly n roots, right? So if you take all the complex roots, the number of complex roots will always be even. So there is at least one real solution for every real polynomial equation of odd degree. So this is something which you need to remember. So in this video, let us look at the theorems regarding repeated roots of a polynomial equation. So the theorem states that a complex number alpha is a repeated root to f of x is equal to 0. A complex number alpha is a repeated root to a polynomial equation f of x is equal to 0 if and only if alpha is a root of f of x is equal to 0 and f dash of x is equal to 0. So if alpha is a root of both f of x is equal to 0 and f dash of x is equal to 0, then alpha will be a repeated root to f of x. And this statement works in both ways. If you have a common root to f of x is equal to 0 and f dash of x is equal to 0, then that root will always be a repeated root to original function f of x is equal to 0. And if alpha is a repeated root to f of x is equal to 0, then it will be a common root to f of x and f dash of x is equal to 0. Let us take an example. Let us see the logic of this. If you have f of x is equal to x minus 2 whole square times x minus 3, something like this, you can see that 2 is a repeated root to f of x. Now, what is f dash of x? So you can differentiate this using product rule, right? X minus 2 whole square times differentiation of x minus 3 is 1 plus x minus 3 times 2 times x minus 2, that is equal to, so x minus 2 whole square, x minus 2, you can take 1 x minus 2 as common. So x minus 2 times x minus 2 plus 2 times x minus 3, that is equal to x minus 2 times 3x minus 8. So as you can see, x minus 2 is a double root of f of x, and you can see that this factor x minus 2 is repeated in f dash of x is equal to 0 also. That means 2 is a common root to both f of x and f dash of x. So this 2 is a repeated root to f of x is equal to 0. So whenever alpha is a repeated root to f of x is equal to 0, that root will be a common root to both f of x is equal to 0 and f dash of x is equal to 0. The next theorem states that all the factors of GCD of f of x and f dash of x, all the factors of GCD of f of x and f dash of x are repeated roots to f of x is equal to 0. So there need not be only one repeated root. Whatever repeated roots are there to f of x is equal to 0, all those roots will be common roots to f of x and f dash of x is equal to 0. So they will be visible in the GCD of f of x and f dash of x. All the factors of the GCD of f of x and f dash of x, that is all the common factors of these two, will be repeated roots to f of x is equal to 0. So these are the two statements which you need to remember. And most usually what happens is, if a root is of multiplicity m to f of x is equal to 0, that root will be of multiplicity m minus 1 to f dash of x. So if f of x is equal to 0 has, if f of x is equal to 0 has a root alpha with multiplicity equal to m, this alpha will be a root of f dash of x is equal to 0 with multiplicity is equal to m minus 1. That means if f of x has x minus 2 whole cube into x minus 3 whole square into x minus 5, f dash of x will at least have an x minus 2 whole square and an x minus 3 times something. So 2 is a root with multiplicity 3 for f of x. 2 will be a root with multiplicity 2 for f dash of x. So this is how usually the pattern looks like. So I hope you have understood the theory of repeated roots. So in this video, let us look at the relation between the roots and coefficients of a polynomial equation. Let us take an example. Let us say that you have a quadratic equation ax square plus bx plus c is equal to 0. And let the roots of this equation be alpha and beta. So ax square plus bx plus c is equal to 0 is a quadratic equation, and let alpha and beta be the roots of this quadratic equation. Now the question is, how do we relate alpha and beta with the coefficients ABC? Obviously, this roots alpha and beta depend in some way on ABC, and if you have roots alpha and beta, they in some way determine the coefficients ABC. So what is the relation between these two quantities? So to understand this, let us do some simplification. So ax square plus bx plus c can be written as, so alpha and beta are the roots of this equation. That means x minus alpha and x minus beta are the factors of this polynomial. And if you write this as x minus alpha into x minus beta, so for these two sides to be equal, what you need to do is you need to equate at least one of the coefficient. So as you can see, you have x square here, you have ax square here. So for those two to be equal, so you just need to put an a here. So ax square plus bx plus c, it has two linear factors x minus alpha into x minus beta. Now if you divide this with x minus alpha and x minus beta, you get the quotient as a. So this is equal to a into x minus alpha into x minus beta. That is equal to a times x square minus of alpha plus beta into x plus alpha beta. That is equal to ax square minus a times alpha plus beta times x plus a alpha beta. Now these two polynomials are equal. So the x square coefficient a should be same as x square coefficient a, and x coefficient b has to be same as the x coefficient here minus a times alpha plus beta. The constant term here c has to be equal to the constant term here a alpha beta. This implies alpha plus beta is equal to minus of b by a. Alpha plus beta is equal to minus of b by a, and alpha beta is equal to c by a. The sum of the roots is equal to minus of x coefficient by the leading coefficient, and the product of roots is the next coefficient by the leading coefficient. That is equal to minus of x coefficient by x square coefficient. That is alpha plus beta. And alpha beta is equal to constant term by x square coefficient. So these are the two relations that you have for a quadratic equation. Now let us do the same analysis for a cubic equation and see what the pattern is. So let us take the equation ax cube plus bx square plus cx plus d is equal to 0. This is a cubic equation. Let the roots be alpha, beta and gamma, as we have done before. So if the roots are alpha, beta, gamma, ax cube plus bx square plus cx plus d can be written as x minus alpha into x minus beta into x minus gamma times a. Because these three are the factors, you can write this as x minus alpha into x minus beta into x minus gamma. For the x cube coefficient on both sides to be same, you need to put an a here. Now these two sides are equal. If I expand this, I get a times, if you multiply these three, you get x cube minus of alpha plus beta plus gamma times x square plus alpha beta plus beta gamma plus gamma alpha times x minus alpha beta gamma. So this is equal to this. So if this is equal to this, let us equate the coefficients. X cube coefficient a is obviously equal to a. Now x square coefficient b is equal to minus a times alpha plus beta plus gamma. C is equal to a times alpha beta plus beta gamma plus gamma alpha. D is equal to minus of a times alpha beta gamma. This implies the sum of all the roots alpha plus beta plus gamma. So sum of all the roots, I'll write it as S1, is equal to minus of second coefficient by first coefficient minus of b by a. Next, what is this? The sum of products of two roots taken at a time. The sum of products of two roots taken at a time. So you have alpha, beta, gamma. In how many ways can you select two roots? I can select alpha, beta, beta, gamma and gamma alpha. So this is nothing but product of two terms and sum of them. Sum of products of two roots taken at a time. So let us write it as S2 is equal to next coefficient by a. And alpha, beta, gamma, I can think of it as sum of products of three roots taken at a time. So if you want to take three roots, I can take it only in one way. So alpha, beta, gamma is equal to minus of d by a, minus of next coefficient by a. So S1 is minus of second coefficient by first coefficient. S2 is plus of third coefficient by first coefficient. S3 is minus of fourth coefficient by first coefficient. So in all these formulas, you divide with the leading coefficient. You have an alternate minus plus sign and the coefficients just go one after the other. So this type of simplification can also be thought for quadratic equation. So in a quadratic equation, you have only two roots alpha plus beta. So S1 is nothing but minus of second coefficient by first coefficient. And S2, sum of products of two roots taken at a time. If you have only two roots, you can take the product only in one way. which is alpha into beta, is equal to next coefficient by a. You have an alternate minus plus. If you have 3 roots, minus plus minus. Next, if you have 4 roots, you'll have minus plus minus plus so on. So let us write the final formula for a general polynomial equation. So if you take a general polynomial equation, an xn plus an minus 1 xn minus 1 plus an minus 2 xn minus 2 so on, a1x plus a0 is equal to 0. So this is an nth degree polynomial equation. So obviously you have n roots, alpha 1, alpha 2, alpha 3 so on up to alpha n. Now S1 for this polynomial equation, S1 is nothing but the sum of the roots is equal to minus of the second coefficient by the first coefficient. S2, the sum of products of two roots taken at a time. Sigma alpha I alpha j is equal to plus of next coefficient by first coefficient. Next, S3, sum of products of 3 roots taken at a time is equal to again minus of next coefficient by first coefficient. This alternate minus plus signs continues. So on, Sn, sum of products of n roots taken at a time, that is nothing but the product of all the roots, is equal to minus 1 whole power n times last coefficient by first coefficient. So this is a general rule for all polynomial equations. So let us take some examples and practice this concept. So the question given is that x cube minus 3x square plus 7x minus 2 is equal to 0 has roots alpha, beta and gamma. You are asked to find alpha square, beta square and gamma square. So how do we do this? So let us write the relations that we know between alpha, beta and gamma. So the sum of alpha, beta and gamma is equal to minus of second coefficient by the leading coefficient, that is minus 3 by 1, which is equal to 3. So alpha plus beta plus gamma is equal to 3. Next, sum of products of two roots taken at a time, alpha beta plus beta gamma plus gamma alpha is equal to plus of next coefficient by first coefficient, that is equal to 7. Next, alpha beta gamma is equal to minus of last coefficient by first coefficient, which is equal to 2. So these are three results that we already know. Now from this, can you find alpha plus beta, alpha square plus beta square plus gamma square? Yes, we can use our very basic formulas that you have learned in lower classes. Alpha plus beta plus gamma whole square is equal to alpha square plus beta square plus gamma square plus 2 times alpha beta plus beta gamma plus gamma alpha. This implies alpha plus beta plus gamma, which is 3 square, 9 is equal to alpha square plus beta square plus gamma square plus 2 times alpha beta plus beta gamma plus gamma alpha is 7. This implies alpha square plus beta square plus gamma square is equal to 9 minus 14 is minus 5. So in this way, using the relations that we have, we can derive various expressions that can be formed using roots. So if you are asked to find alpha cube plus beta cube plus gamma cube, apart from this, you are also asked to find this. So how do we do? So So we can use our formulas. Alpha cube plus beta cube plus gamma cube minus 3 alpha beta gamma is equal to alpha plus beta plus gamma times alpha square plus beta square plus gamma square minus alpha beta minus beta gamma minus gamma alpha. So this implies alpha cube plus beta cube plus gamma cube. This is what we need to find out. Alpha cube plus beta cube plus gamma cube minus 3 alpha beta gamma. Alpha beta gamma is 2 minus 3 into 2 is 6 is equal to alpha plus beta plus gamma 3 times alpha square plus beta square plus gamma square. I've already found it. Minus 5 minus of alpha beta plus beta gamma plus gamma alpha. If you take a minus common, so you get 7. So this implies alpha cube plus beta cube plus gamma cube is equal to 7, 5 minus 12 into 3 minus 36 plus 6, which will be equal to minus 30. So alpha square plus beta square plus gamma square is minus 5. Alpha cube plus beta cube plus gamma cube is minus 30. So similarly, you can find various expressions which are formed out of alpha, beta, gamma. So in this question, you're given a cubic equation x cube minus px square plus qx minus r is equal to 0. And it is given that the roots are alpha, beta, gamma. And two of its roots, alpha and beta, satisfy the condition alpha plus beta is equal to 0. If that is so, what is the relation that should be present between P, Q, R? So obviously for any three numbers P, Q, R, alpha plus beta need not be equal to 0. Now it is given that this equation satisfies this condition. That means there should be some sort of relation between P, Q, R for this to be true. What is the condition? So how can we do this? This equation has roots alpha, beta, gamma. So now let us try to write the relations that we know between alpha, beta, gamma. So one of the basic relation is alpha plus beta plus gamma is equal to alpha plus beta plus gamma is equal to minus of second coefficient by first coefficient minus p by 1, which is equal to p. Now it is given that alpha plus beta is equal to 0. So this is equal to 0. This implies the third root gamma has to be equal to p. The third root gamma has to be equal to p. That means this root p has to satisfy this equation. And this implies the condition is nothing but p cube minus p times p whole square plus q times p minus r is equal to 0. So p cube and p cube gets cancelled. This implies p cube minus r is equal to 0. So this will be the condition that should connect P, Q, R so that this relation is valid. In this question, you're given a cubic equation x cube minus px square plus qx minus r is equal to 0. You're given that the roots of this equation are in HP, harmonic progression. And you're asked to show that the mean root, that is the root in between, is 3r by q. And using the results that you get from the above, you're asked to solve 6x cube minus 11x square minus 3x plus 2 is equal to 0. So x cube minus px square plus qx minus r is equal to 0. Let the roots of this equation be alpha, beta and gamma. Now it is given that the roots are in harmonic progression. That means 2 by beta is equal to 1 by alpha plus 1 by gamma. So this is the condition which is given. Now, what are the conditions that we know for this equation? Alpha plus beta plus gamma is equal to minus of second coefficient by first coefficient, which is equal to P. Alpha beta plus beta gamma plus gamma alpha is equal to Q. Alpha beta gamma is equal to R. So these are the three conditions which we already know. This is the condition which is given. So let us try to simplify this condition and see with which condition is this closely related to. So 2 by beta is equal to gamma plus alpha by alpha gamma. This implies 2 alpha gamma is equal to alpha beta plus gamma beta. So you can very clearly see that this condition is more related to this condition. So given that alpha beta plus gamma beta, alpha beta plus beta gamma, alpha beta plus beta gamma is equal to 2 alpha gamma. This implies the sum of this is 2 alpha gamma plus alpha gamma. So 3 alpha gamma is equal to Q. This implies alpha into gamma is equal to Q by 3. Now, I have this relation, I have this relation. Let us see these two relations and get some simplifications out of this. Alpha into gamma is Q by 3. This implies beta times Q by 3 is equal to R. This implies beta is equal to 3R by Q. Beta is equal to 3 into R by Q, where beta is the mean root, that is the root in between, and this is found out to be 3R by Q. So this is proved. Now, this 3R by Q is a solution to this equation. 3R by Q is a root to this equation, hence this has to satisfy this equation. So let us find a condition. So this implies x cube 27R cube by Q cube minus P times x square is 9R square by Q square plus Q times x is 3R by Q minus R is equal to 0. So this is the condition which relates P, Q and R. So let us simplify this. So 27R cube minus 9 PQR square plus 3R Q cube, 3R Q cube minus R Q cube is equal to 0. R Q cube is equal to 0. So 3R Q cube minus R Q cube is 2R Q cube. This implies 27R cube minus 9 PQR square plus 2R Q cube is equal to 0. 1R will get cancelled. So the effective condition is 27R square, 27R square minus 9 PQR plus 2Q cube is equal to 0. So this condition 27R square minus 9PQR is good, plus 2Q cube is equal to 0. Yes. So this is the condition which needs to be valid if the roots are in HP. If you compare this equation with this equation, so what is the value of P? The value of P is 11 by 6, because in the given equation there is the leading coefficient is 1. So if you want to compare these two equations, you need to divide this equation by 6. So P is equal to 11 by 6 by comparison, Q is equal to minus 3 by 6 and R is equal to minus 2 by 6. So corresponding to this PQR, let us see if this condition is valid. So 27 times R square, R is minus 1 by 3, whole square is 1 by 9. Minus 9 times P times Q times R plus 2 times Q cube. So as you can see, you get 3 minus 11 by 4 minus 1 by 4 is equal to 0. So for this equation, this condition is getting valid. That means the roots of this equation are in harmonic progression, and the mean root, which is beta, is equal to 3r by q. So one of the root of this equation is 3 times r is minus 1 by 3 by q is minus 1 by 2. So minus and minus gets cancelled, 3 and 3 gets cancelled, is equal to 2. That means 2 is one of the root of this equation. So let us divide this equation with x minus 2 and get the quotient, right? Let us get the quadratic quotient, which we can solve easily. So let us use our Horner's synthetic division. So you have 6 minus 11 minus 3, 2, and the root is 2 because the factor is x minus 2. So I'll write plus 2 instead of minus 2. So let us do the division. 6 2s are 12, 1 2s are 2, minus 1 minus 2, so the remainder is 0, and the quotient is 6x square plus x minus 1. You can very easily do the factorization for this. So minus 6 can be written as plus 3x minus 2x plus 3x minus 2x minus 1. This implies 3x times 2x plus 1 minus 1 times 2x plus 1. This implies 2x plus 1 times 3x minus 1 is equal to 0. So the roots are minus 1 by 2 and 1 by 3 and 2. So these are the 3 roots to this equation. Look at the interesting topic of transformation of roots of a polynomial equation. So let us take an example and see what we are trying to do in this topic. So let us take an example. So if you have an equation x square minus 5x plus 6 is equal to 0. So let us take a very simple quadratic equation. X square minus 5x plus 6 is equal to 0. So the roots of this equation, as we know, are 2 and 3, because this is x minus 2 into x minus 3 is equal to 0. Now let us say that you're asked to find an equation, you're asked to find a quadratic equation whose roots are double the roots of this equation. You're asked to find a quadratic equation whose roots are double the roots of this equation, that is 4 and 6. So how do we find the equation? So the process is like this. Okay, the roots of this equation, let us say that the roots are alpha comma beta. Now I want the equation whose roots are 2 alpha and 2 beta. So let us take a variable y is equal to 2x. Let us take a variable y is equal to 2x. So let us say that x is a root of this equation. Let us say that x is a root of this equation. Now I want an equation whose roots are y, because y is equal to 2x. So if x is a root of this equation, I want an equation whose roots are y. That means I want a condition which y satisfies. Specifically, I want a quadratic condition which y satisfies. So to find that is very easy. So let us see how to do this. So y is equal to 2x. This implies x is equal to y by 2. And my x is a solution to this equation. That means this y by 2 satisfies this equation. So let us put y by 2 in the place of x. So you get y by 2 whole square minus 5 times y by 2 plus 6 is equal to 0. This implies y square by 4 minus 5y by 2 plus 6 is equal to 0. This implies y square minus 10y plus 24 is equal to 0. So this is a quadratic condition which y satisfies, and y is nothing but 2 times the number which satisfies this equation. Hence, this is an equation whose roots are 2 alpha and 2 beta. So if you want an equation in x, finally you can put x in the place of y. So x square minus 10x plus 24 is equal to 0 is an equation whose roots are 2 times 2 and 2 times 3, that is 4 and 6. You can check for yourself. So this is nothing but x minus 4 times x minus 6, right? So the roots are 4 and 6, which you're asked to find. So effectively, what have you done? So if you want an equation whose roots are 2 times the roots of the original equation, you just need to put y by 2 in the place of x. That is the reverse of that. If you want the roots to be double, you have to put y by 2 in the place of x. If you want the roots to be triple, so the condition, if you want the roots to be triple, so we take y is equal to 3x and x is equal to y by 3. So if you want the roots to be 3 times, you have to put x is equal to y by 3. So this is a general process in which we transform the roots. So let us take another example. X cube minus 3x square plus 5x plus 2 is equal to 0. So this is a cubic equation. Let the roots of this equation be alpha, beta and gamma. Let the roots of this equation be alpha, beta and gamma. Now I want an equation, a cubic equation, whose roots are 2 greater than the roots of this equation. It means I want an equation whose roots are alpha plus 2, beta plus 2 and gamma plus 2. I want to increase the magnitude of the roots by 2 units. So how do I do it? So again, let us say that x is a solution to this equation. Now I want, so let me say y is equal to x plus 2. So x is a root of this equation. I want an equation whose roots are y. That is, I want a cubic condition which y satisfies. So how do I get this? So y is equal to x plus 2 implies x is equal to y minus 2. X is equal to y minus 2. So let us put x is equal to y minus 2 in here. So y minus 2 whole cube minus 3 times y minus 2 whole square plus 5 times y minus 2 plus 2 is equal to 0. So you just need to expand this. So y cube minus 3y square times 2, that is 6y square plus 3 into 2 square, 3 4s are 12y minus 8 minus 3y square plus 12y minus 12 plus 5y minus 10 plus 2 is equal to 0. This implies y cube minus 6y square minus 3y square is minus 9y square. 24y plus 9y plus 5y, that is 29y. 8 minus 20 minus 30 plus 2 is minus 28 is equal to 0. So this is a condition in y, and y is nothing but x plus 2. That means if x is a root of this, x plus 2 will be a root of this. So this is an equation whose roots are 2 greater than the roots of this equation. So I hope you understand what we are doing. We are just substituting the reverse function in the place of x. So if you want the roots to be greater by 2, you have to substitute y minus 2. If you want the roots to be lesser by 2, you have to substitute y plus 2 in the place of x, so on. So let us take some standard transformations and see the substitutions that you need to do to get the required transformations. So let us look at some standard transformations and the standard substitutions that need to be done so that we get the transformations. So first, if you have an original equation whose roots are alpha, beta, so on. Now, if I want my roots to be transformed to some k times alpha, k times beta, so on. That means if I want my roots to be multiplied or divided by some number. So if you want to multiply the roots by some number, the substitution that you need to do is y by k in the place of x. So if you want to multiply by 2, you have to write y by 2. If you want to multiply by 3, you have to write y by 3. If you want to multiply by 1 by 3, that is, if you want to divide by 3, you have to multiply by 3 here. So whatever you do here, you have to do the opposite when you do the substitution. Next, when you want to add certain number to all the roots, if you want to increase the magnitude of all the roots by a number k, you have to substitute y minus k in the place of x. Y minus k in the place of x. Next, if you want to raise all the roots to some power n, you have to substitute nth root of y in the place of x. Because y is equal to x power n implies x is equal to nth root of y. Next, if you want the roots to be reciprocals of the original roots, y is equal to 1 by x. This implies x is equal to 1 by y. So you need to substitute 1 by y in the place of x. If you want the roots to be of negative signs of the original roots, so y is equal to minus x implies x is equal to minus y, right? So you just need to put minus y in the place of x. So these are some very standard substitutions that leads to very standard transformations. So if you have some complicated transformations, you just need to use this process. Whatever is the transformation, you need to write y is equal to some sort of transformation in x. And you have to find what x is in terms of y. And you need to substitute this in the place of x. So let us take some more examples. So let us take this example. X cube minus 5x square plus 2x minus 3 is equal to 0 has roots alpha, beta and gamma. You are asked to find the equation whose roots are alpha by 1 plus alpha, beta by 1 plus beta and gamma by 1 plus gamma. So how do we transform the original roots into these roots? So as you can very clearly see, the transformation, if this number is x, the transformation is of the form x by 1 plus x, is same for all the roots. So you have to have the same transformation for all the roots. Then only we can use the theory of transformation of roots. So let us take y is equal to x by 1 plus x. So if x is a root of this equation, you want an equation whose roots are of the form x by 1 plus x. So y is equal to x by 1 plus x. I want a condition, cubic condition in y. So this implies y plus xy is equal to x. I'll try to find what x is. This implies y is equal to x minus xy. That is equal to x times 1 minus y. And this implies x is equal to y by 1 minus y. So if y is equal to x by 1 plus x, x has to be equal to y by 1 minus y. But we know that x satisfies this equation. This implies y by 1 minus y whole cube minus 5 times y by 1 minus y whole square plus 2 times y by 1 minus y minus 3 is equal to 0. Y by 1 minus y whole cube minus 5 times y by 1 minus y whole square plus 2 times y by 1 minus y minus 3 is equal to 0. So this is the required equation in y whose roots are these three. Now we just need to simplify these roots. So let us take the LCM. So you get y cube minus 5y square times 1 minus y plus 2y times 1 minus y whole square minus 3 times 1 minus y whole cube is equal to 0. So you just need to simplify and collect the terms. Y cube minus 5y square plus 5y cube plus 2y cube plus 2y minus 4y square minus 3 plus 3y cube minus 3y, so plus 9y minus 9y square is equal to 0. So you just need to collect the terms y cube, 5y cube, 2y cube, 3y cube. So 7, 10, 11. So 11y cube and minus 5y square minus 4y square minus 9y square minus 9y square is minus 18y square. So these three are completed. So 9y plus 2y is 11y. 9y plus 2y is 11y. And minus 3 is equal to 0. So this is the required equation. So in this video, let us look at a shortcut to increase the roots by a fixed number. For example, if you have a polynomial a0 x power n plus a1 x power n minus 1 plus a2 x power n minus 2 plus so on up to an is equal to 0. If the roots of this equation are alpha 1, alpha 2, so on up to alpha n. Now let us assume that I want an equation whose roots are alpha 1 plus k, alpha 2 plus k, alpha 3 plus k, so on up to alpha n plus k. That means I want an equation whose roots exceed the roots of this equation by a constant k. So we have already seen the substitution that we need to do. So what is the substitution that we need to do? So we take y is equal to x plus k and substitute x with y minus k. So the required equation is, a0 times y minus k power n plus a1 times y minus k whole power n minus 1 plus a2 times y minus k whole power n minus 2 plus so on plus an is equal to 0. Now the problem with this is that we need to expand each of this and collect the corresponding coefficients. So let us say that we have done all of that. So let us say that this is equal to some capital A0 times yn plus capital A1 times y power n minus 1. So let us say that we have collected all the coefficients correspond to y power n and the corresponding coefficient is A0. I have collected all the coefficients correspond to y power n minus 1 and the corresponding coefficient is capital A1 plus a2 times y power n minus 2 plus so on up to an minus 1 into y plus an is equal to 0. So let me write a coefficient just before this an. Now your aim is to find a0, a1, a2, an minus 1 and an. So usually you'll be asked to expand this to find this a0, a1, so on. Let us take an example to see the difficulty here. So if you have an equation of the form x power 5 plus 2x power 4 plus 5x cube minus 4x plus 6 is equal to 0. If you want an equation whose roots are, so if this equation has roots this, if you want an equation whose roots are exceeding the roots of this equation by 2. So what you need to do is, you need to put y minus 2 in the place of 5. So y minus 2 power 5 plus 2 times y minus 2 power 4 plus 5 times y minus 2 whole cube minus 4 times y minus 2 plus 6 is equal to 0. So till this point it is easy, but to expand this is not very easy. So you have to expand y minus 2 power 5. So you get y power 5, y power 4, y cube, y square, y at constant term. Here also you get a lot of terms. Here also you get a lot of terms, so on. And you need to collect all those terms. After collection, you might get some number times y power 5 plus some other number times y power 4 plus some other number times y cube plus some number times y square plus some other number times y plus some number is equal to 0. So if you can have a shortcut to derive these numbers, that would be very useful. So now let us see how we can easily derive these numbers using Horner's synthetic division. So now we have understood that we need some process to find these capital A0, A1, A2, so on. So how do we do this? So now what we do is, let us do the back substitution again. Now if I want to convert this equation into the original equation again, if I want to convert this equation into the original equation, what is the substitution that I need to do? So in the original equation, I substituted x is equal to y minus k to get this equation. So in this equation, if you substitute y is equal to x plus k again, you get the original equation, right? So original equation can be found out by putting y is equal to x plus k again. So a0 times x plus k power n plus a1 times x plus k whole power n minus 1 plus a2 times x plus k whole power n minus 2 plus so on plus an minus 1 times x plus k plus a. This is exactly same as the original equation. So this implies the original equation can be written as x plus k times a0 times x plus k whole power n minus 1 plus a1 times x plus k whole power n minus 2 plus so on up to an minus 1 plus a. So the original equation can be written as x plus k times this plus a. So can you see that if I divide the original equation by x plus k, the remainder is nothing but the last number. The remainder is nothing but the last number a. So dividing by x plus k is very easy. To find the remainder is also very easy. Now once you get an, the quotient is nothing but this. The quotient is this. So in the quotient, you get an minus 2 times x plus k again. So if you divide this again by x plus k, now the remainder will be the next coefficient. And you get some quotient. And if you divide it again by x plus k and find the remainder. So successively if you find the remainders of the quotient by dividing with x plus k, at each stage you get the numbers starting from the last coefficient to the first coefficient. So this is the process which we do to get this a0, a1, a2, so on up to an minus 1 very easily. So let us apply this process and see the beauty of this process. So as the first example, let us take the same question that we have already solved in the previous section. X cube minus 3x square plus 5x plus 2 is equal to 0 is the equation whose roots are alpha, beta, gamma. And you're asked to find the equation whose roots are alpha plus 2, beta plus 2 and gamma plus 2. So if you want the coefficients of the required equation, you just need to divide this equation by x plus 2 successively and find the remainders in each case. So let us use Horner synthetic division for this. 1 minus 3, 5, 2. You need to divide by x plus 2, right? You need to divide by x plus 2. So we use minus 2 here because we need to change the coefficient of the constant term. You need to change the sign of the constant term. So let us start doing this. So 1 minus 2 is minus 2, minus 3 minus 2 is minus 5, minus 5 into minus 2 is 10. So you get 15. 15 into minus 2 is minus 30. Hence, the first remainder is minus 28. The remainder of the first stage is minus 28. That means the last coefficient is minus 28. Now let us continue this process again. So again let us divide with minus 2. So 1 into minus 2 is minus 2. Minus 5 minus 2 is minus 7. Minus 7 into minus 2 is plus 14. And the remainder in the next stage is 29. Now let us continue the process. Again we'll divide with minus 2. So you get 1 here. So 1 into minus 2 is minus 2. The remainder is minus 9. And the last remainder is 1. So now that means the required equation is nothing but 1x cube minus 9x square plus 29x minus 28 is equal to 0. So you can see that this type of process is very simple. But this can be used only for the special case of transformation where you need to add some number to the roots or subtract some number to the roots. So let us take few more examples to demonstrate this process. The more the degree of the equation is, the more easiness this process brings to the solution. In this example, you have a 5th degree equation. 2x power 5 minus 6x power 4 plus 5x cube minus 2x square plus 6 is equal to 0. And the roots of this equation are alpha i's. That is alpha 1, alpha 2, alpha 3, alpha 4 and alpha 5. You are asked to find the equation whose roots are alpha I minus 3. That means you are asked to reduce the magnitude of the roots by a constant 3. So how do we get the coefficients correspond to the transformed equation? We just need to divide this successively by x minus 3. So divide original equation successively by x minus 3. So let us use Horner's process again. So 2 minus 6, 5 minus 2, 0, 6. You don't have an x coefficient, you need to write a 0. Now if you want to divide by x minus 3, you need to use plus 3 here, right? So 2 3s are 6, 0, 0 3s are 0, 5 3s are 15, minus 2 plus 15 is 13, 13 3s are 39, 0 plus 39 is 39, 39 into 3 is 90 plus 27, 117. So 117 plus 6 is 123. So that will be the constant term of the required equation. Now again let us go forward. Let us again divide by x minus 3. So you have a 2 here. Let us write a 3 again. So 2 3s are 6. So you get a 6. 6 3s are 18. 18 plus 5 is 23. 23 into 3 is 69. 69 plus 13 is 82. And 82 into 3, 246. So 246 plus 39, we get 285. We got the next coefficient. Now let us again go forward. Again let us divide by x minus 3. So you get a 2 here. 2 3s are 6. 6 plus 6 is 12. 12 3s are 36. 36 plus 23 is 59. 59 into 3 is 150 plus 27. 177. So 177 plus 82, that is 259. 259. So let us again do the same process. So 2 3s are 6. Get 18 here. 18 3s are 54. 18 3s are 54. You get 100 plus 13, 113. So coming to the final stage, again we divide by 3. Shift 2 here. 2 3s are 6. So 18 plus 6 is 24. So you got all the coefficients starting from the highest coefficient to the lowest coefficient. So the required equation is nothing but 2x power 5 plus 24x power 4 plus 113x cube plus 259x square plus 285 times x plus 123 is equal to 0. So this particular question would have been very cumbersome if we use the standard process. That is, if you directly try to put y plus 3 in the place of x and try to simplify this will be a very big question which is very difficult to simplify. But using Horner's synthetic division, we have very easily solved this question. So if you want to diminish the roots by k, divide by x minus k. If you want to exceed the roots, that is, if you want to make the roots as alpha plus k, you have to divide by x plus k. And when you divide, we know that you need to change the sign of the constant term so that the process instead of subtraction will become addition. So I hope you have understood this easy shortcut. So in this video, let us look at the topic of symmetric expressions of roots. So what are symmetric expressions? The expressions where each root of the equation have same importance is called a symmetric expression of roots. For example, if you take a cubic equation whose roots are alpha, beta and gamma, so we can form different expressions using this three roots, like alpha beta plus beta gamma plus gamma alpha. So this is an example of a symmetric expression of alpha, beta and gamma. So why is it called so? Because in this expression, each of these roots have exactly the same importance. Alpha is occurring twice, beta is occurring twice, gamma is occurring twice. And even if you exchange any two roots, that is, in the place of alpha you write beta, in the place of beta you put alpha. So let us see what happens. So if you exchange alpha and beta, so what does the expression become? Beta alpha plus alpha gamma plus gamma beta. So do you see that this expression is exactly same as this expression? Yes. Alpha beta plus beta gamma plus gamma alpha again. In the same way, if you exchange beta and gamma, instead of alpha beta, you exchange beta with gamma. So what happens? Alpha gamma plus gamma beta plus beta alpha. Again, you get the same expression. So the expressions like these, where on interchanging any of the two roots, the expression does not change, is called a symmetric expression. Symmetric expression. Now, these symmetry expressions are usually written in sigma form. So if you want alpha beta plus beta gamma plus gamma alpha, instead of writing this whole thing, we write this simply as sigma alpha beta. So when you write sigma alpha beta, you should understand this as alpha beta plus beta gamma plus gamma alpha. So now let us take another example. Again, if you have alpha, beta, gamma as the roots, let us take a cubic equation again. Now if I write sigma alpha square beta, sigma alpha square beta, what does this represent? So if you expand this, how many terms are there in this expansion? So to find that, we can use the theory of permutations and combinations. So in this expression, if you take a single term, you have one root to the power 2 and the other root to the power 1. So effectively, we need to choose one of this root. We need to select one of the root and give a square to it. And out of the remaining two roots, you need to select one of the root and give a power of 1. So in how many ways can you do this? So one root can be selected from these three roots in 3C1 ways. So let me select one of these in 3C1 ways and give it a square. And so one of this has been consumed. Now there are two remaining roots. And out of these two remaining roots, I need to select one of them. So that is 2C1 ways. So that is equal to 3 into 2 is equal to 6. So you have 6 different ways in which you can write expressions of the type alpha square beta. So this expansion contains 6 different terms. So alpha square beta plus beta square alpha plus alpha square gamma plus gamma square alpha plus beta square gamma plus gamma square beta. So corresponding to alpha square, you can have beta as well as gamma. Corresponding to beta square, you can have alpha as well as gamma. Corresponding to gamma square, you can have alpha as well as beta. So this is same as this. Next, if you have 4 roots alpha, beta, gamma and delta, and with respect to these 4 roots, if you want to write sigma alpha beta. So in how many different ways can you write sigma alpha beta? This is same as selection of 2 roots out of 4 roots. Selection of 2 roots out of 4 roots. So in how many ways can you select 2 roots out of 4 roots? 4C2 ways. That is equal to 6 ways. So this expansion contains 6 different terms. Something like alpha beta plus beta gamma plus gamma delta plus delta alpha plus alpha gamma plus beta delta. So these are the 6 different terms that come in sigma alpha beta. Alpha beta, alpha gamma, alpha delta, beta gamma, beta delta and alpha delta. So if you have sigma alpha square beta, so how many terms does this expansion have? So here you need to select one root to give a square and you have to select another root to give a power 1. So in how many ways can you do this? Initially, you have to select one of the root to give a square. So you can do it in 4C1 ways. And once you select a root and give it a square, Now 3 terms are left. So out of these 3, you need to select one in 3C one ways. So you have a total of 12 terms if you expand this. Sigma alpha square beta has 12 terms. So if you want sigma alpha square beta gamma, so how many terms does this expansion have? So here what we need to do is we need to select one of them to give a square power, and we need to select two of them to give a single power. So in how many ways can you do this? 4C1 ways in which you can select one of the root to give a square, and out of these remaining 3 you need to select two of them. So into 3C2. So again you have 12 terms in this. You have 12 terms in this. So if you want sigma alpha beta gamma, if you have 4 roots and if you want to write sigma alpha beta gamma, how do we write it? So all the powers are 1. So effectively we need to select 3 roots out of this 4 roots. We need to select 3 roots out of this 4 roots. So in how many ways can it be done? 4C3 ways, which is equal to 4. So sigma alpha beta gamma contains 4 different terms. So I hope you understand how to see the number of terms that are present in different sigmas. And using the relation between the coefficients and the roots of a polynomial equation, we can find the values of many symmetric expressions. So let us take some examples and find the values of symmetric expressions. Let us take this example. X cube minus 3x square plus 4x minus 2 is equal to 0 has roots alpha, beta and gamma. This cubic equation has roots alpha, beta and gamma. In that case, you are asked to find sigma alpha square beta, sigma alpha square, sigma alpha cube, sigma alpha square beta square, sigma alpha cube beta square. So let us see how to find this. So sigma alpha square beta. So what does this sigma represent? First let us try to find the number of terms in this sigma. So here you need to select one root for a square power and one root for a 1 power. So in how many ways can you select one of these 3C1 ways I can select one root for my square power, and once I select these 3, one root is consumed. Next there are 2 roots which are left. Out of these 2 I need to select one of them, that is 2C1 ways. So you have a total of 6 terms in this expansion. And what is the meaning of sigma alpha square beta? This is nothing but alpha square beta plus alpha square gamma plus beta square alpha plus beta square gamma plus gamma square alpha plus gamma square beta. So this is the sum which you need to find. So to find this sum, so what are the things that I know beforehand? So I know the relation between the roots and the coefficients. So what are the given relations? Alpha plus beta plus gamma is equal to minus of second coefficient by first coefficient, which is equal to 3. And alpha beta plus beta gamma plus gamma alpha is equal to plus next coefficient by first coefficient, it's 4. And alpha beta gamma is equal to minus of last coefficient by first coefficient, which is equal to 2. So these 3 are the known relations. So using these 3, can you find this? So this is equal to, so now if you take this expression alpha square beta and beta square alpha. So in these two expressions I can take alpha beta as common, If I take alpha beta as common, I get alpha plus beta. Next, alpha square gamma and gamma square alpha. If I take this term and this term, so I get alpha gamma as constant. Alpha gamma is a common term, so alpha plus gamma. Plus finally, beta square gamma plus gamma square beta. So gamma beta times gamma plus beta. So that is equal to, now alpha beta times, what is alpha plus beta? Alpha plus beta is 3 minus gamma. Plus alpha gamma times, what is alpha plus gamma? 3 minus beta. Plus gamma beta times gamma plus beta is 3 minus alpha. So that is equal to, so you have 3 alpha beta, 3 alpha gamma plus 3 gamma beta. That is 3 times alpha beta plus beta gamma plus gamma alpha minus alpha beta gamma, alpha beta gamma, alpha beta gamma is 3 times alpha beta gamma. That is equal to 3 times, this expression is known, which is 4, minus 3 times alpha beta gamma is 2. So 3 4s are 12, minus 3 2s are 6. So you get 12 minus 6 is equal to 6. So sigma alpha square beta is equal to 6. Next, so if you want sigma alpha square, so this is very straightforward. You have only one root here. So in how many ways can you write terms like this? So you need to select one out of 3 terms, that is 3C1 ways. So you have 3 terms here, alpha square plus beta square plus gamma square. So using these 3, how can you find this? So alpha square plus beta square plus gamma square is nothing but alpha plus beta plus gamma whole square minus 2 times alpha beta plus beta gamma plus gamma alpha. That is equal to sigma alpha, alpha plus beta plus gamma is 3. So 3 square is 9 minus 2 times sigma alpha beta is nothing but alpha beta plus beta gamma plus gamma alpha. This is equal to 4. So 9 minus 8 is equal to 1. So sigma alpha square is equal to 1 here. Next, if you want sigma alpha cube, so how can we get this? So there are different ways in which you can get this, but one of the ways, so alpha cube, sigma alpha cube is nothing but alpha cube plus beta cube plus gamma cube. This can be written as alpha plus beta plus gamma times alpha square plus beta square plus gamma square minus, so alpha cube, beta cube, gamma cube. What are the extra terms you get? Alpha beta square plus alpha square beta, beta gamma square plus gamma square beta, and alpha square gamma plus gamma square alpha. This is nothing but the first expression, right? Minus sigma alpha square beta. So alpha cube plus beta cube plus gamma cube is sigma alpha times sigma alpha square minus sigma alpha square beta. That is equal to sigma alpha is 3, sigma alpha square, which is equal to 1, minus sigma alpha square beta, which we have already found out as 6. So 3 minus 6 is equal to minus 3. So I hope you are understanding how to find different symmetric expressions. The basics that we need to use are the relations known to us. And from these relations, we get all the relations that we want. So next, sigma alpha square beta square is nothing but sigma alpha square beta square is nothing but, so out of these 3 roots, you are selecting 2 roots for square. So how many ways can you select 2 roots out of 3 roots? 3C2 ways. That is 3 ways. So this expansion contains three terms: alpha square beta square plus beta square gamma square plus gamma square alpha square. So you have three possible terms. Now, so how do we get the summation of this? So this can be written as sigma alpha beta whole square. It is alpha beta plus beta gamma plus gamma alpha whole square minus 2 times sigma alpha beta square gamma. That is minus 2 times this. So alpha beta whole square is alpha beta plus beta gamma plus gamma alpha whole square is equal to, this is square plus this square plus this square, plus 2 times alpha beta square gamma plus beta gamma square alpha plus gamma alpha square beta. That can be written as this. So that is equal to, what is sigma alpha beta? Sigma alpha beta is alpha beta plus beta gamma plus gamma alpha, which we have already seen as 4. So you get 16 minus. So what is the summation of this? So 2 times, if you expand this, you get 3 terms. Sigma alpha beta square gamma, you get 3 terms, out of which you get alpha beta is common. So there is nothing but alpha beta gamma times alpha plus beta plus gamma. That is 2 times alpha plus beta plus gamma is 3. So that is equal to 16 minus 12, which is equal to 4. So sigma alpha square beta square is equal to 4. Next, sigma alpha cube beta square. So how many terms does this expansion have? So you need one root to be selected to give a power of 3 and another root to be selected to give a power of 2. So one root can be selected in 3C1 ways, and from the remaining 2, one root can be selected in 2C1 ways. So 3 2s are 6. So we have a total of 6 terms. So what are the 6 terms? Alpha cube beta square plus beta cube alpha square plus beta cube gamma square plus gamma cube beta square plus gamma cube alpha square plus gamma square alpha cube. So these are the 6 terms that you have. So how do we add this? So you can take alpha square beta square as common. So alpha square beta square times alpha plus beta plus beta square gamma square times beta plus gamma, alpha square gamma square times alpha plus gamma. That is equal to alpha square beta square times alpha plus beta, as we have seen before, alpha plus beta plus gamma is equal to 3. So alpha plus beta is 3 minus gamma plus beta square gamma square times 3 minus alpha plus alpha square gamma square times 3 minus beta. That is equal to 3 times sigma alpha square beta square, right? 3 times alpha square beta square plus beta square gamma square plus gamma square alpha square minus, as you can see, alpha square beta square gamma, alpha beta square gamma square, alpha square beta gamma square. So if you take each of this term, so you can take alpha beta gamma as common in each of this. So alpha beta gamma, if you take it as common, you get alpha beta here, beta gamma here, gamma alpha here. That is sigma alpha beta. That is equal to 3 times sigma alpha square beta square, we have already found as 4, minus alpha beta gamma is 2 and sigma alpha beta is 4. So 12 minus 8 is again equal to 4. So sigma alpha cube beta square is also equal to 4. So in this way we can find the values of different symmetric expressions in roots. Let us look at the Descartes rule of signs. So this rule says that a polynomial equation polynomial equation f of x is equal to 0 with real coefficients, cannot have more positive roots than the number of changes of sign in f of x is equal to 0. A polynomial equation f of x with real coefficients cannot have more positive roots than the number of changes of sign in f of x is equal to 0. That is, if you have 3 sign changes in f of x is equal to 0, the polynomial equation f of x is equal to 0 cannot have more than 3 positive roots. And the second statement is that the polynomial equation with real coefficients cannot have more negative roots than the number of changes of sign in f of minus x is equal to 0. So these two statements combinedly form the Descartes rule of signs. So a polynomial equation f of x is equal to 0 with real coefficients cannot have more positive roots than the number of changes of sign in f of x is equal to 0. And they cannot have more negative roots than the number of changes of sign in f of minus x is equal to 0. So let us first see what change of sign means. So what is meant by change of sign? So if you write f of x, if you write the real polynomial f of x in the increasing order of the powers of x or decreasing order of powers of x, that is, you need to write in one specific order. If you write f of x in increasing order of powers of x, if the sign of coefficients change from plus to minus or minus to plus, then we say that a change of sign has occurred. A change of sign has occurred. So if f of x is written in increasing powers of x, if the sign of coefficients change from plus to minus or minus to plus, then we say that a change of sign has happened. For example, if you have 2x cubed plus x minus x square minus 3 is equal to 0. So if this is my f of x, first what I do is I'll arrange this equation in increasing powers of x or decreasing powers of x. That is 2x cubed minus x square plus x minus 3 is equal to 0. Now let us write the signs of the coefficients. That is, the first coefficient is positive, the second coefficient is negative, the third coefficient is positive, the fourth coefficient is negative. Now start from the first sign. So plus has changed to minus. You have one change of sign. The minus has again changed to plus. You have the second change of sign. The plus has again converted to minus. You have the third change of sign. So you have 3 changes of sign in this polynomial. You have 3 changes of sign in this polynomial. So if you have 2x cubed plus x square minus x minus 3 is equal to 0. So here the signs of the coefficients are plus, plus and minus, minus. Now how many changes of sign are there in this equation? So plus to plus, there is no change of sign. Plus to minus, there is one change of sign. Minus to minus, there is no change of sign. So there is a total of one change of sign. That means, according to Descartes' rule, this equation cannot have more than one positive root. This equation cannot have more than one positive root. The polynomial cannot have more positive roots than the number of changes of sign in f of x is equal to 0. So if you see the second statement, a polynomial equation cannot have more negative roots than the number of changes of sign in f of minus x is equal to 0. So if this is f of x is equal to 0, what is f of minus x? You just need to put minus x in the place of x. So if you put minus x in the place of x, you get minus 2x cube plus minus x whole square is x square. Minus of minus x is plus x. Minus 3 is equal to 0. So what are the signs of the coefficients? Minus, plus, plus, minus. Minus, plus, plus, minus. So you have one change of sign here, no change of sign, another change of sign. So you have a total of two changes of sign. That means this equation 2x cube plus x square minus x minus 3 cannot have more than two negative roots. That means all the roots of this equation cannot be negative. And this can have at most one positive root and at most two negative roots. So this is what Descartes' rule of signs say. So let us take another example. In this question, you're given that if a greater than 0, prove that this cubic equation x cube plus ax plus b is equal to 0 has two complex roots. So how do we do this? So let us use our Descartes' rule of signs. So there are two cases, right? A is given as positive. B can be either positive or negative. So let us take the case 1. If b is greater than 0, then what is our conclusion? So if b is greater than 0, from the Descartes' rule of signs, the signs of coefficients of f of x is nothing but plus, plus and plus, because 1 is positive, a is positive, and we have assumed that b is positive. So plus, plus and plus. There are no change of signs. Hence, f of x cannot have positive real roots, because the maximum number of positive real roots to the equation f of x is equal to 0 is the number of changes of sign in f of x. There are no changes of sign in f of x, hence the equation f of x is equal to 0 cannot have positive roots. Next, consider f of minus x. F of minus x is nothing but minus x cube, and if you put minus x in the place of x, you get minus ax plus b. So what are the signs of this? Minus, minus and plus. Now how many changes of sign are there? You have no change here, one change here. So one change of sign. You have only one change of sign. This implies f of x can have a maximum of one negative root. So it cannot have any positive roots, and it can have a maximum of one negative root. It can have a maximum of one negative root. This implies f of x can have a maximum of one real root. So positive roots and negative roots constitutes all real roots. So can have a maximum of only one real root. But in a total, this equation has 3 roots. So what should be the remaining 2 roots be? So this implies f of x has a minimum of 2 non-real complex roots. So it has to have at least 2 complex roots, because complex roots always occur in pairs. All 3 cannot be complex. So it should have a minimum of 2 complex roots, and it has 2 complex roots, because all the 3 roots cannot be complex. Complex roots always occur in conjugate pairs. So if b greater than 0, we have proved that this equation has 2 complex roots. Next, what if b less than 0? If b less than 0, the signs of f of x are plus, plus, minus, positive, positive and negative. So one change of sign, one COS change of sign. This implies a maximum of one positive root. Now f of minus x is nothing but minus x cube minus ax plus b, but b is negative, so you have all negative signs. So no change of sign. This implies no negative roots. So have a maximum of one positive root and no negative roots. So which implies that, what does this imply? This implies that a maximum of one real root, and this implies a minimum of 2 complex roots. This implies exactly 2 complex roots, because it cannot have 3 complex roots. So complex roots always occur in pairs. So a minimum of 2 complex roots for a cubic equation means that it has exactly 2 complex roots. So using Descartes' rule of signs, we have deduced that this sort of equation always have 2 complex roots. So in this video, let us look at the salient features of the graphs of polynomial functions. So till now we have discussed polynomial equations. Now we introduce a new concept called polynomial functions and discuss the relation between this function and the equation. So let us take a simple example. So let us take a polynomial equation f of x is equal to 0. So let us take an example, x square minus 5x plus 6 is equal to 0. This is a quadratic polynomial equation. Now corresponding to this equation, this is my f of x. If I define a function y is equal to f of x, this is called a polynomial function. That is, y is equal to x square minus 5x plus 6. So this is called a polynomial function. A polynomial equation has solutions. A polynomial equation has solutions or roots. So we solve a polynomial equation and get the solutions of the polynomial equation or roots of the polynomial equation. But we don't solve a function. A function is some sort of a rule which connects x to y. We substitute different values of x and you get different values of y. A function is some sort of a rule which connects x to y. So a function has a graph. An equation does not have a graph. An equation has a solution. An equation has roots. A function does not need to be solved. A function is some sort of rule which connects x and y. A function corresponds to a graph, and f of x is equal to 0 is an equation, y is equal to f of x is a function. Now if you draw the graph of this polynomial function, this is an example of a polynomial function. This is a quadratic. You can have any degree polynomial function. So one of the first thing that you need to observe about polynomial graphs are that the graphs of polynomial functions are continuous. That is, the graphs don't break anywhere. They go continuously without breakages. They go continuously without breakages. Second, as x tends to plus or minus infinities, as x tends to plus or minus infinities, f of x or y also tend to plus or minus infinities. So as x goes to infinities, y's also go to infinities. They can go to plus infinity or minus infinity anywhere, depending on the leading coefficients and the powers of the leading coefficients and the degree of the equation. So depending on leading coefficient and degree of f of x. This is the second thing to observe. So as you can very clearly see here, if x tends to infinity, at x is equal to infinity, these two terms will not matter much. Only the highest power of x matters. As x tends to infinity, y tends to infinity square, which is infinity. If x tends to minus infinity whole square is again equal to plus infinity. That means as x goes to minus infinity or plus infinity, y goes to plus infinity. The third thing to observe is the relation between polynomial equation and the polynomial function. The roots of polynomial equation, the values of x where f of x is equal to 0, are the abscissa of points where the graph cuts x-axis. Because if this graph cuts x-axis, that means y is equal to 0, and the values of x where this y is equal to 0 are nothing but the roots of this equation. X square minus 5x plus 6 is equal to 0. So wherever that happens is the solution of this equation. So the roots of f of x is equal to 0 are nothing but the abscissa of the points where the graph cuts x-axis. For example, if you take this, the roots are 2, 3. At x is equal to 2 and x is equal to 3, y will be equal to 0. That means if you draw the graph of this, this is 2, this is 3. So 2 and 3 will be the abscissa of the points where this graph meets x-axis. So the graph will look something like this. The graph goes to plus infinity as x tends to minus infinity as well as plus infinity. And they meet x-axis at the points which are roots of this equation. So the roots of f of x is equal to 0 are abscissa of the points where the graph cuts x-axis. Next property is that if at 2 points A and B, let this be the point A, let this be point B. If at any 2 points A and B, the sign of f of x changes. So if between any 2 points the sign of f of x changes, that means if f of A times f of B is negative, if f of a times f of b is negative. That means if f of a is positive, f of b is negative or negative positive. So if at a and b the values of f of a and f of b change sign, then how should the graph look like? So if f is positive at a and negative at b, so what are the different possibilities for graphs between a and b? Because the polynomial graphs are continuous, they have to be continuously moving from this point to this point. So the graph can go like this. That means it has to cut the x-axis at some point between a and b. Or the graph can be something like this. It can go down, go up, and then come down to this point. That means the graph is cutting the x-axis at 3 points between a and b. Or it can move like this. That means the graph is cutting the x-axis at 5 points between a and b, or 7 points, or 9 points, so on. So if f of a into f of b is negative, then there should be odd number of roots to f of x is equal to 0 between a and b. So between a and b, f of x is equal to 0 should have odd number of roots, that is 1 root or 3 roots or 5 roots, so on. Similarly, if a and b are 2 points such that the sign of f of x don't change between a and b, if the sign does not change, means if you have a point A and a point B, so this is f of A and this is f of B. So what might happen between A and B? The graph is continuous, it does not get broken at any point. So the graph can directly go like this, where you don't have any root between A and B. Or it can come down and go like this, where it has 2 zeros between A and B. It can come down, go up, come down, and then go up here, which means that there are 4 roots between A and B, so on. So if the sign does not change between A and B, that is f of A into f of B is greater than 0, this implies f of x is equal to 0 has even number of roots between A and B. So I hope this statements are clear. If f of A and f of B have opposite signs, then there should be odd number of roots between A and B. If f of A into f of B is greater than 0, then there should be even number of roots between A and B. So next, there is a theorem called Rolle's theorem, which says that between any 2 roots of y is equal to f of x. So if you have a polynomial function y is equal to f of x, and if you have 2 numbers a and b, where f of a is equal to 0 and f of b is equal to 0. That means if the graph passes through these 2 points, then between these 2 points, f dash of x will be equal to 0 at least 1 point. So if a and b are the zeros of y is equal to f of x, or a and b are the roots of f of x is equal to 0, then f dash of x will be equal to 0 at least once between a and b. That means if you draw the graph between a and b, the graph has to go up and come down, right? So f dash of x will be equal to 0 at least 1 point somewhere in between a and b. It can be 0 more than once also. So if you have a graph which looks like this, it is 0 at this point, 0 at this point, 0 at this point. So if you can have more peaks and more troughs, you can have more number of solutions to f dash of x is equal to 0. So between two zeros of the function f of x is equal to 0, between two roots of the equation f of x is equal to 0, f dash of x will be equal to 0 at least once, or more specifically odd number of times. At least once between a and b, or more specifically odd number of times between a and b. So either once or 3 times or 5 times or 7 times, so on. So this is called Rolle's theorem. And a corollary to this theorem is that between two consecutive roots of f dash of x is equal to 0, between two consecutive roots of f dash of x is equal to 0, f of x is equal to 0 has at most one root. F dash of x is equal to 0 has at most one root between two consecutive roots of f dash of x is equal to 0. That means, let us say that f dash is equal to 0 at a and b. That means the tangent is parallel to x-axis, or the graph becomes flat at these 2 points. Assume that the graph becomes flat like this, and the next consecutive root is like this. So you cannot have two consecutive maximas. So here, if it is maxima, the next consecutive root should correspond to a minima. So if the graph is like this at a and like this at b, if you connect these two, because b is a and b are consecutive roots of f dash of x is equal to 0, in between a and b, f dash of x is not equal to 0. So they have to get directly connected. So here, as you can see, there is no root for f of x is equal to 0 between a and b. In the next case, if at x is equal to a and x is equal to b, the graph is like this at a, and the graph is like this at b. And in between a and b, f dash of x is not 0, and it directly goes down and meets this trough. Here, as you can see, f of x is equal to 0 has exactly one root between a and b. So these are the only two cases which are possible. So if you have two consecutive roots of f dash of x is equal to 0, between a and b, there can be at most one root for f of x is equal to 0, right? And when will you get a root and when will you not get a root? So if both this f of a and f of b are of same sign, then you won't get any root between a and b. If f of a and f of b are of opposite signs, then you get exactly one root between a and b. So between two consecutive roots of f dash of x is equal to 0, f of x is equal to 0 has at most one root, and more specifically, no root if f of a into f of b is positive. That means both at a and b, f has same sign, and one root if f of a into f of b is negative. So I hope this is clear. If f dash of x is equal to 0 at 2 points, such that these 2 points have the functional values of opposite signs, then you have exactly one root between a and b. If both are of same sign, both are positive or both are negative, if you join like this, both are positive and both are negative, then also you won't have any root between A and B. So this is a very powerful theorem which can be used to see how many roots, how many real roots a cubic equation has. So let us consider this example. So 2x cube minus 9x square plus 12x minus k is equal to 0 is a cubic equation where this k is an unknown. So you are asked to find k so that all the roots are real. So what should be the value of, what should be the interval in which k has to lie so that all the roots of this equation are real? That means this equation should have 3 real roots. So that means if you draw the graph of this function, it has to cut the x-axis at 3 distinct points. So the graph has to be like this. Now if the graph has to be like this, what should be the condition? So first what I do is, I'll solve the equation f dash of x is equal to 0. So I'll see where the differentiation of this equation is 0. So 6x square minus 18x plus 12 is equal to 0. That is x square minus 3x plus 2 is equal to 0. So x minus 2 times x minus 1 is equal to 0. X is equal to 1 or 2. That means at x is equal to 1 and at x is equal to 2, f dash of x is equal to 0. That means at x is equal to 2 and x is equal to 1, f dash of x is equal to 0. Now, what should happen if all the 3 roots have to be real? So between these two, you should have one real root, right? Between these two, you have one root, because between any two consecutive roots of f dash of x is equal to 0, you can have at most one root. And after this, you can have one root, and before this, you can have the other root. Now, for all the 3 roots to be real, the simple condition is that at x is equal to 1 and at x is equal to 2, the functional values have to be of the opposite signs. So what is f of 1? F of 1 is nothing but 2 minus 9 plus 12 minus k. That is equal to 14 minus 9, 5 minus k. Now what is f of 2? F of 2 is 2 into 8, 16 minus 9 into 4, 36 plus 12 into 2, 24 minus k. That is equal to 24 plus 12 is 36. So you have a 4 extra. 4 minus k is f of 2. Now f of 1 and f of 2 should be of opposite signs. So this implies 5 minus k times 4 minus k has to be less than 0. Has to be less than 0. This implies 5 minus k into 4 minus k is less than 0. This implies k minus 4 times k minus 5 is less than 0. So from wavy curve analysis, 4, 5, wavy curve looks like this. So I want the negative interval. This implies k has to belong to 4 to 5. So if k belongs to 4 to 5, f of 1 and f of 2 will be of opposite signs. Then you get one root between 1 and 2, the other root between 2 and infinity, and the third root between minus infinity to 1. So you can also check that this is valid, because if k is in between 4 and 5, f of 2 will be negative, f of 1 will be positive. So we have a graph like this, and you have all the three roots as distinct and real. So if you don't need the roots to be distinct, if you just want them to be real, you can consider closed 4 to 5 also. And if you want real and distinct, you have to consider open 4 to 5. So if you consider closed 4 to 5, then f of 1 into f of 2 will be equal to 0. That means at one of these points, the graph is going to 0. That means the graph looks like this. So one of the root will be a double root. One of the root will be a double root. So I'll mostly prefer open 4 to 5 if the roots are to be real and distinct. So in this question, you're asked to analyze the nature of roots of this equation. You have a 4th degree equation. You're asked to find how many of the roots of this equation are real and how many are imaginary. To understand this, so let us go for the differentiation of this function. So f dash of x is nothing but 12x cube plus 12x square minus 12x minus 12. So let us try to solve f dash of x is equal to 0. That means where are the stationary points for this function? This implies if you take 12 outside, x cube plus x square minus x minus 1 is equal to 0. So this can be very easily factorized because the sum of coefficients is equal to 0 and the sum of the odd power coefficients and the sum of even power coefficients is also equal to 0. This means x plus 1 is also a factor and x minus 1 is also a factor. Effectively, x square minus 1 is a factor to this equation. And what is the remaining quotient that you get? So you can use Horner's synthetic division. So 1, 1, minus 1, minus 1. So first let us divide with x minus 1. So let us use 1 here. So 1, 1, 2, 2, 1, 1. So you get 0. So next let us divide with x plus 1. So let us use minus 1 here. 1, minus 1, 1, minus 1. You get remainder 0. And the quotient is x plus 1. So the third factor is x plus 1. So f dash of x is equal to 0 implies x plus 1 whole square times x minus 1 is equal to 0. This implies x is equal to minus 1 or plus 1. So once we have solved f dash of x is equal to 0, let us try to analyze the graph of this function. So if you draw the rough graph of this function, as x tends to infinity, f of x also tends to plus infinity. At x is equal to infinity, y is infinity. And when x is equal to minus infinity, also y is plus infinity, because the leading coefficient is positive and the degree is even. Now at x is equal to minus 1 and plus 1, f dash of x is equal to 0. So what is f of minus 1? At x is equal to minus 1, what is the functional value? So f of minus 1 is equal to 3 minus 4 minus 6 plus 12 plus 2. So as you can see, the number is a positive number. That means at x is equal to minus 1, the functional value is positive. That means you have an answer which is above x-axis. Next, what is f of plus 1? What is f of plus 1? 3 plus 4 minus 6 minus 12 plus 2. So minus 18 plus 9 is less than 0. It means at x is equal to plus 1, the functional value is negative. So now let us combine all the information that we have to see how the graph looks like. The graph starts from infinity here. It becomes stationary here. Means it becomes somewhat stationary here. And then the next stationary point is at x is equal to 1. But the value at x is equal to 1 is negative. That means the graph has to cross x-axis from this point to this point. It becomes stationary here. And then it has to reach plus infinity. So it has to move up and go up. So this is how the graph has to be shaped. Hence, as you can see here, the graph cuts x-axis at exactly 2 points. That means this equation has 2 real roots. That means this is a 4th degree equation. If it has 2 real roots, that means it has to have the other 2 as